Hello there, and welcome to Science for Sleep, where curiosity curls up beside comfort and the universe becomes a place not to solve, but to gently wander through. Tonight, I'd like to take you on a slow and quiet drift through the galaxy we call home, and then beyond it, toward the enormous, humbling, and almost impossible shapes that fill the cosmic deep. You and I, right now, are sitting somewhere inside a glowing river of starlight called the Milky Way, surrounded by more stars than we could ever count, and yet, in the grand map of the universe, our home is only a small patch of brightness in an ocean so vast it barely registers as a glimmer. Before we begin this long, slow journey, I wonder where you're listening from tonight. Is it quiet where you are? Maybe the soft hum of a night lamp nearby, or the stillness of a room that's finally settled down for the evening. Perhaps you're lying back with your eyes closed, letting your mind loosen its grip on the day. Or maybe you're the kind who likes to picture things as they unfold, seeing the shapes in your imagination. Wherever you are, and whatever time it happens to be for you right now, that's exactly where this story starts. Not out in the stars, but right here, with you. If you find these cosmic rambles a comforting way to fall asleep, or just a pleasant way to slow down, I'd be grateful if you gave this a little like or maybe subscribe to join more of these calm explorations. It helps this space of quiet science reach others who might need a soft voice drifting through their own night. Now, settle in. Let your shoulders drop, take a slow breath, and imagine this. Above you, far above the clouds and the thin blue line of our atmosphere, the Milky Way stretches across the night sky. A faint milky band that humankind has looked at for as long as we've had eyes to look up. To the naked eye, it's just a pale smear, but through the lens of science, it's a spiral of hundreds of billions of suns. Every pinprick of light you see is just one small beacon inside it, like a lantern on a dark sea. When you see a photograph of it, the Milky Way often looks like a swirl painted on black velvet, its arms curling around a bright core. But that's not how we see it from Earth. From inside, it's more like looking through the trees of a forest. The branches of stars stretch in every direction, and no matter where you turn, there's more light behind it. If you could step outside and look back, if you could somehow travel far enough away to see our galaxy as a whole, you'd see something with an elegance that borders on simplicity. A disk about 100,000 light-years across, rotating gently like a slow-spinning coin, its spiral arms rich with gas, dust and star clusters that glimmer faintly against the dark. That's home. One galaxy among billions, orbiting quietly in a cosmic neighborhood that we call the local group. It's easy to think of it as enormous, and to us, it absolutely is. Everything we have ever known, every person, every life, every story, has unfolded in a tiny corner of one of those arms, a mere 25,000 light-years from the center. But if we lift our gaze just a little higher, if we stretch our imagination a little farther, we begin to see that our galaxy is not a giant at all. It's more like a middleweight, a standard model, a kind of average spiral that sits comfortably between the small and the colossal. You can picture it like this. Imagine the universe as an endless city at night. Every galaxy is a glowing window, some small and faint, others vast and brilliant. The Milky Way is one of those steady, medium-bright windows. Beautiful, certainly, but not the biggest, not the most extravagant. Somewhere out there, in that same endless city, are structures so enormous that even light, which moves faster than anything else we know, takes millions of years just to cross them. Those are the giants of the universe, galaxies that dwarf ours, galaxies with 10 times, even 100 times more stars, galaxies so large that the Milky Way would fit inside them several times over, with room to spare. It's hard to think about that scale without the mind slipping a little. Numbers start to lose their meaning. 100 billion stars feels abstract. 1 trillion stars feels almost fictional. Yet those are the kinds of numbers that define the biggest galaxies in existence. To compare ours with theirs is like comparing a glowing campfire with a city seen from orbit. Both beautiful, both made of the same light, but living on vastly different scales. And yet, there's something strangely reassuring about that. Because in a universe filled with extremes, with objects that defy the limits of size and brightness, our galaxy feels balanced. It's not too big to be chaotic, not too small to fade away. It's stable, star-forming, quietly turning for billions of years. It's the kind of galaxy where life had time to appear, where the long, slow unfolding of complexity was possible. Maybe that makes it ordinary in cosmic terms, but extraordinary in human ones. As we wander through this story together, we'll look at what makes a galaxy what it is, how ours compares to its neighbours, and what happens when you venture out to meet the giants, the cosmic cities that make our Milky Way seem like a quiet town. But we'll move slowly. The universe isn't in a rush, and neither are we. Between each idea there's space to breathe, to let the mind settle, to imagine the distances and the light. Think of this as a slow flight outward, from home to horizon. We'll begin with the familiar, the spiral we call home, and gradually drift toward the edge of what we can know, where galaxies blur into clusters and clusters melt into filaments of light stretched across the cosmos. You don't need to remember every number or name. Just let them pass by like constellations seen from a train window, one after another, softly glowing. Out there, somewhere, are galaxies that make ours look like a single grain of dust in a beam of sunlight. Galaxies that have swallowed others whole, that have grown in the centres of massive clusters until they became the anchor points of entire regions of space. They're strange to imagine because their scale no longer fits inside the normal frame of human thought. You could take every star in the Milky Way and repeat it hundreds of times, and still they'd shine brighter. But even those vast structures are still small in comparison to the universe itself, which stretches far beyond anything we've seen, filled with light that has travelled for billions of years just to reach our telescopes. So tonight, as you rest, we'll take our time wandering among them. We'll look at what it means for a galaxy to be large, what kind of forces shape them, and what it says about our place that we live inside one that's perfectly ordinary by cosmic standards. We'll see how galaxies form, how they grow, and how they sometimes collide, merging into new shapes that continue to spin and shine for billions of years. The universe has a rhythm of its own, slow, patient, unhurried. Galaxies are its quiet dancers, moving to a beat that stretches across time. As we drift from thought to thought, you might find your own rhythm slowing to match it, your breathing deepening, your awareness softening. That's all right. That's what this space is for. The universe can wait for your thoughts to catch up. When we talk about the Milky Way, we're not really talking about a thing we can ever see in its entirety. We're inside it, wrapped up in its glow, looking outward through layer upon layer of starlight and dust. Every direction we turn, we're staring through thousands of light years of stars, each one part of an immense pattern we can't step back far enough to view. The Milky Way is like a city you've lived in all your life but have only ever seen from street level. You can sense its structure, the long avenues of stars, the bustling core, the quieter outskirts, but you'll never see the whole skyline all at once. Astronomers have spent decades piecing that skyline together, not through a single image, but through evidence, data, radio waves, and infrared maps. The shape that emerges from all that information is a spiral, not a perfect one, more like a living thing with arms that twist and drift slightly unevenly, as if sculpted by time and motion rather than drawn by a ruler. 4 major arms, they say, along with smaller spurs and bridges that link them, each filled with clouds of gas and dust and clusters of newborn stars. The Sun, and therefore we, are part of a small spur between 2 of those main arms, a quiet suburb, far from the bright restless centre. If you could rise above it all and look down, the Milky Way would stretch roughly 100,000 light-years across. That's a number we can say easily but can't really feel. 1 light-year is about 9.5 trillion kilometres, so 100,000 of them means the Milky Way spans nearly a quintillion kilometres from one edge to the other. It rotates too, completing one slow turn every 230 million years or so. In the time since the dinosaurs first appeared, the Sun has made only a single lap around the galaxy. Right now, as you listen, we're drifting at about 220 kilometers per second along that orbit, and yet everything around us feels perfectly still. The heart of the Milky Way is a place we can't see directly because it's shrouded by dense clouds of interstellar dust. But hidden in that darkness is a region of intense energy known as Sagittarius A, a supermassive black hole about 4 million times the mass of our Sun. It's not the kind of monster that devours everything nearby in a single gulp. It's relatively calm, quietly feeding on occasional gas clouds that wander too close. Around it, stars orbit at dizzying speeds, some completing their loops in just a few years. These stars have allowed astronomers to measure the black hole's mass precisely, confirming that it's the gravitational anchor of the galaxy. Surrounding that invisible centre is a bulge, a thick, crowded region of older stars that glows in golden light. Beyond that, the spiral arms sweep outward, each one a blend of ages. The arms aren't fixed structures like the arms of a windmill. They're more like traffic patterns, regions where stars and gas bunch up due to waves of density moving through the disk. New stars form within these waves, lighting them up, then drift away, leaving behind faint traces that slowly fade as the stars age. The arms are like cosmic rivers, always changing, always flowing, never quite the same from one moment to the next, though that moment might last millions of years. If you picture the Milky Way as a glowing disk, there's also a faint spherical halo surrounding it. This halo contains ancient stars, globular clusters, and a great deal of invisible dark matter. That dark matter, though unseen, makes up most of the galaxy's mass, shaping its motion and holding it together. Without it, the stars in the outer regions would be moving too fast. They'd simply fly away into the void. Dark matter, whatever it is, acts like a silent scaffolding, giving the galaxy its structure, unseen but essential. From our position within one of the spiral arms, about halfway between the centre and the edge, the night sky appears rich and crowded. If you've ever looked up on a dark, clear night far from city lights and seen that faint white band crossing the heavens, you've glimpsed the Milky Way from the inside. What you're seeing is the combined glow of hundreds of millions of distant stars, their light blurred together by distance, and even then, you're seeing only a small slice, just a few thousand light-years deep before dust blocks your view. If you could see the rest, it would wrap around the entire sky like a soft, endless ring. It's humbling to think that our solar system is just one among hundreds of billions inside this vast structure. Some estimates suggest there might be 100 to 400 billion stars in the Milky Way, and likely even more planets, perhaps trillions. Among them, billions could be roughly Earth-sized, orbiting in conditions where liquid water might exist. Somewhere out there, other worlds may circle their suns, perhaps with their own versions of night skies, their own quiet observers wondering if they're alone. In that sense, our galaxy isn't just a structure of stars, it's a potential cradle of countless unknown lives. When astronomers measure the light from the Milky Way, they find it's a typical example of a spiral galaxy. It's not especially large compared to others, nor particularly small. Its diameter, its star count, its rotation speed, all fall near the middle of the galactic range. There's comfort in that ordinariness. It means our home is stable, balanced, not too violent or chaotic. Some galaxies burn too brightly, forming stars at a furious pace and then exhausting their gas quickly. Others are quiet and dim, their star-forming days long over. The Milky Way sits in between, forming a few new stars every year, enough to keep it alive and glowing, but not enough to tear itself apart. Our galaxy is surrounded by smaller companions, faint dwarf galaxies that orbit it like satellites. The two most prominent are the large and small Magellanic Clouds, visible from the southern hemisphere as hazy patches of light. These small galaxies are slowly being pulled apart by the Milky Way's gravity, leaving trails of gas that wrap around us like invisible ribbons. Over time, they may merge completely, adding their stars to our own. This slow gathering of smaller galaxies has been happening throughout the Milky Way's history. It's one of the ways galaxies grow, not just by forming new stars, but by absorbing their neighbours. If you could watch the Milky Way's life in fast forward over billions of years, you'd see it as a dynamic, evolving thing. Streams of gas flow inward, feeding new generations of stars. Clusters of stars move like schools of fish, following gravitational tides. Tiny galaxies fall in, stretching and blend in until they disappear. The spiral pattern flickers and shifts, and through it all the galaxy spins, a slow, steady rotation that has continued for more than 10 billion years. It's both ancient and alive, changing constantly, but never losing its form. We tend to imagine galaxies as isolated, floating alone in the void. But the Milky Way, like most galaxies, is part of a community. Around 30 galaxies make up what we call the local group, a small cluster of cosmic neighbours bound together by gravity. The Milky Way and the Andromeda Galaxy are the two largest members, like twin anchors holding the group in place. Between them lie smaller galaxies, each with its own shape, history and motion. Some are bright enough to be seen with a small telescope, others so faint that only deep surveys reveal them. The stars we see overhead are all part of the Milky Way's disk, but if you could step back far enough, you'd see that disk set against the larger structure of the universe, clusters of galaxies connected by filaments of dark matter and gas, forming a web that spans billions of light years. Our galaxy is just one node in that web, glowing quietly amid a network of cosmic light. From where we sit, we can study only parts of it directly. Dust and gas block much of the visible light, so astronomers use other wavelengths, infrared, radio, and X-rays, to peer through the obscuring layers. Radio telescopes can map the distribution of hydrogen gas, tracing the spiral arms. Infrared observations can see through the dust to reveal stars in the centre. X-rays show regions of high energy, where black holes and neutron stars release bursts of radiation. Together, these different views combine like layers of a painting, revealing a galaxy alive with activity. It's easy to think of the Milky Way as static, as though it's been this way forever, but in cosmic terms, it's a work in progress. Its oldest stars, found in globular clusters, are more than 12 billion years old, nearly as old as the universe itself. Those stars formed when the galaxy was still taking shape, merging from smaller protogalaxies in the early universe. Over time, it gathered more gas, built its spiral disk, and began the long, rhythmic process of star birth and death that continues today. Every star you see in the night sky is part of that cycle. Each one was born from clouds of hydrogen and helium that collapsed under gravity. Many will eventually die in brilliant supernova explosions, scattering heavy elements, carbon, oxygen, iron, into space. Those elements mix with new clouds, forming new generations of stars and planets. In that way, everything you see, including yourself, is made of material forged inside earlier generations of stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stars that lived and died long before the sun existed. The Milky Way is not just our home, it's our origin story written across the sky. Even though we can't leave it, not yet, we've begun to map it from within. Space probes and telescopes have given us a three-dimensional sense of where we are. The Gaia spacecraft, launched by the European Space Agency, has measured the positions and motions of over 1 billion stars, creating the most detailed map of the Milky Way ever made. From that data, scientists can trace how the galaxy moves, where stars were born and how they drift over time. It's like watching the slow breathing of an immense luminous organism. And while it feels like we're at the centre of our own perspective, we're not at the centre of the galaxy. We're out on one of the arms, about halfway out from the core, in a region that astronomers sometimes call the Orion Arm or Orion Spur. It's a quiet place, not too crowded, not too sparse. The perfect environment for a stable solar system to evolve without constant gravitational disturbances. If we were closer to the centre, the sky might blaze with the light of millions of nearby stars, beautiful but chaotic. Out here, in the suburbs, the nights are dark enough for life to unfold in relative calm. Our galaxy's beauty lies partly in that balance. Active but not violent, luminous but not blinding, grand but not overwhelming. Its spiral structure is both delicate and enduring, a reminder that even in the vastness of space, order can emerge from chaos. Gravity, gas and time work together to weave a pattern that lasts billions of years, and we happen to be living inside it, a tiny part of its story, looking up and wondering. When you leave the familiar spiral of the Milky Way behind in your imagination, the first thing that fades is the sense of scale. From inside, everything feels infinite, yet the moment you step beyond its edge, it becomes a single object among many. The universe is not empty. It's not even quiet if light could make a sound. It's filled with structures so large and numerous that our galaxy, the one we think of as vast, becomes one among billions. Every direction you look, with a telescope sensitive enough to see far enough back in time, reveals the same sight. Tiny flecks of light scattered across blackness. Each one, almost without exception, is a galaxy. To stand outside it in thought is to understand just how common galaxies are. When astronomers first began pointing powerful telescopes into patches of sky that looked empty, what they found changed our sense of existence completely. The Hubble Deep Field, a small, almost random area of sky no larger than a grain of sand held at arm's length, revealed thousands of galaxies in a single image. Each one carried hundreds of billions of stars. That picture, and the ones taken since, gave us a statistical truth that's almost impossible to hold in the mind. The observable universe likely contains around 2 trillion galaxies, 2 trillion separate collections of stars, gas, dust, and dark matter, each orbiting a centre of gravity, each glowing across time and distance. If you were to drift through space and pass them one by one, you'd find an extraordinary variety. Some are smooth, nearly spherical, with stars packed tightly in their centres. Others are flat and delicate, shaped like the spirals you see in textbooks. Some are irregular, stretched and distorted by past collisions. There are galaxies that blaze with new star formation, their clouds lit up by ultraviolet light, and galaxies so old and red that no new stars have formed there in billions of years. Each one is an ecosystem of gravity, light and time. The term galaxy itself comes from the Greek word galaxias, meaning milky, a reference to that faint band of light our ancestors saw in the night sky. For a long time, people thought that band was the entire universe. Even as telescopes improved, astronomers assumed that all the faint patches of light they saw were part of one grand structure, the Milky Way itself. It wasn't until the early 20th century that this idea was overturned. In 1924, Edwin Hubble used the Mount Wilson Observatory to study a fuzzy object in the constellation Andromeda. By identifying individual variable stars within it and measuring their distances, he proved that the object lay far outside our galaxy. It wasn't a cloud or a cluster within the Milky Way. It was another galaxy entirely, a separate island universe. That realization expanded our cosmos overnight from one galaxy to countless others. Since then, the idea of galaxies as islands has remained one of the most helpful ways to picture the universe. Each is bound together by gravity, surrounded by the dark sea of space, and separated from its neighbours by enormous gulfs of emptiness. The nearest major galaxy to us, Andromeda, is about 2.5 million light-years away. The light we see from it tonight left when early humans were still using stone tools. Between here and there lies almost nothing, a thin haze of hydrogen, a few scattered stars and dark matter we can't see. These distances are so immense that even at the speed of light, a message from one galaxy to another would take millions of years to arrive. Despite that, galaxies are not isolated forever. Gravity is patient. Over cosmic timescales, it pulls them toward one another. Groups form, then clusters, then superclusters, immense gatherings of thousands of galaxies bound together in webs that stretch across the observable universe. Our own Milky Way sits within a small local group, which itself is part of a larger structure called the Virgo supercluster. Beyond that, even larger patterns appear, like filaments connecting clusters into a vast cosmic web. Between these filaments are enormous voids, regions where almost no galaxies exist, great cosmic hollows spanning hundreds of millions of light-years. The universe at its larger scale looks less like scattered points and more like a sponge or a web, with galaxies concentrated along thin threads and walls, and darkness filling the spaces between. When astronomers map these structures, they use the light from millions of galaxies to trace out the shape of everything. Each point on the map represents not a single star, but an entire galaxy, and together they reveal the large-scale geometry of the universe, a pattern born from the tiny fluctuations in the density of matter after the Big Bang. Those fluctuations, amplified by gravity over billions of years, became the seeds of galaxies and clusters. Every spiral, every elliptical, every faint smudge of light owes its existence to that ancient pattern. Galaxies are not static things. They live, in a sense, though their lives play out on scales too long for us to witness. They form from collapsing clouds of gas and dark matter. They grow by accreting smaller systems. They change shape when they collide with others. They form stars in great bursts, then settle into quieter phases. Eventually, many fade as their gas supply dwindles. Some become elliptical galaxies, vast, smooth, featureless swarms of old stars. Others, like ours, remain disc-shaped and continue making new stars for billions of years. The sea of galaxies is full of variety, but certain patterns appear again and again. The most common type by number are the small dwarf galaxies, some with only a few million stars. They're often irregular in shape, vulnerable to the gravitational influence of their larger neighbours. They orbit the giants like tiny moons. The largest galaxies, by contrast, are often elliptical, with trillions of stars and diameters that can exceed 1 million light-years. Between those extremes are the graceful spirals like the Milky Way and Andromeda, moderate in size, rich in gas, and actively forming stars. If you were floating far from any galaxy and looked around, the darkness would seem almost total. Yet if your eyes could detect all wavelengths of light, you'd see that space is faintly glowing. Every direction is filled with the combined light of billions of galaxies. That glow, stretched and softened by distance, is part of what we call the cosmic background, a reminder that wherever you look, the universe is populated. There is no direction that doesn't eventually end at another island of stars. In many ways, galaxies are the universe's way of organising matter. Without them, gas would be too thinly spread for stars to form. Gravity gathers material together until it collapses, ignites, and begins to shine. Once a galaxy forms, it becomes a kind of self-sustaining cycle. Dying stars return material to the interstellar medium, enriching it with heavier elements. That material forms new stars, planets, and everything else that follows. Over time, the chemical richness of galaxies increases, allowing for more complex worlds and possibly life. Some galaxies are surprisingly small and faint. The ultra-diffuse galaxies discovered in recent years are as large as the Milky Way, but contain only a tiny fraction of its stars, making them almost invisible except through long exposures. Others are so compact and bright that they resemble single stars even through powerful telescopes. Some host enormous black holes at their centres that shine as quasars, outshining entire galaxies for a time before fading as their fuel runs out. The diversity is staggering. When you try to imagine the sea of galaxies, it helps to think of them not as scattered dots, but as parts of a continuous structure, connected by invisible threads of gravity. The universe is expanding, yes, but on smaller scales, galaxies within clusters are still bound together. They orbit, interact, and sometimes merge. In those collisions, their shapes distort, spiral arms twist, and vast tidal tails of stars are flung into space. What looks serene from far away is, up close, an ongoing process of creation and change. The light from these galaxies carries stories that are almost too old to believe. When we observe distant ones, we're seeing them as they were billions of years ago, because their light has taken that long to reach us. The farther we look, the younger the universe we see. Some of the most distant galaxies appear as they did only a few 100 million years after the Big Bang, small and irregular, still assembling. Observing them is like looking through a time machine, watching cosmic history unfold frame by frame. The galaxies nearby, like Andromeda or the Magellanic Clouds, show us the middle age of the universe, mature and stable. Together, these views let scientists piece together how galaxies grow and evolve. The scale of the galactic sea also changes how we think about perspective. We often imagine ourselves as tiny because the universe is large, but that largeness is simply the natural result of its age. Light travels at a finite speed, and gravity works slowly. Over billions of years, small differences in density became enormous structures. Our galaxy's size, about 100,000 light-years across, is just what gravity and time produce when matter has had 13 billion years to gather. The fact that it feels large to us is more about our own scale than anything else. Still, the immensity of it can be soothing in its own way. When you realise that every star you see belongs to one galaxy, and every patch of sky hides millions more, the universe begins to feel less like an empty void and more like an endless community of light. Each galaxy is far apart, yet all share the same physical laws, the same ingredients, the same origin. The hydrogen in distant galaxies is the same hydrogen in our own. The processes that form stars and planets are universal. In that sense, the sea of galaxies is a kind of unity, diversity built from sameness. As you imagine drifting farther, leaving the local group behind, you would eventually come to the Virgo cluster, a great congregation of over 1,000 galaxies bound together by gravity. Many of them are ellipticals, massive and ancient, sitting at the cluster's heart. Around them are smaller spirals and irregulars, swirling like minnows around whales. Beyond that cluster lies another and another, until the clusters form filaments stretching across the observable universe. If you could see it all at once, the pattern would resemble a vast luminous web. This web is sometimes called the cosmic large-scale structure. It's the skeleton of the universe, shaped by dark matter and expanded by dark energy. The galaxies are like bright dust caught along its threads. Where filaments intersect, clusters form. Where matter is thin, voids open up. Enormous regions where there are few galaxies at all. The largest of these voids are hundreds of millions of light-years across, nearly empty of everything but a faint trace of hydrogen. To cross one would take longer than the history of life on Earth, and yet even the emptiness serves a purpose. It's part of the balance that allows galaxies to exist. Matter flows along gravitational gradients from voids to filaments, feeding clusters and sustaining the process of structure formation. The universe is not static, but always rearranging itself, slowly, subtly, on scales too vast for us to feel. From a distance, the Milky Way is one drop in this cosmic ocean, its light indistinguishable from millions of others. But from within, it's home, familiar and complete. That duality, of being both ordinary and extraordinary, is something that seems to echo through the universe itself. Every galaxy is unique in detail, yet common in design. Every light is personal from up close, anonymous from afar. The sea of galaxies is full of such contrasts. As we continue our quiet drift through it, the question naturally arises: where does our Milky Way stand among all these others? How does our spiral compare to the largest and brightest islands in this cosmic archipelago? What makes some galaxies grow so large that they contain 10 times as many stars as ours, their light visible across hundreds of millions of light years? To answer that, we have to keep moving outward, past the ordinary spirals, toward the colossal forms that dominate the clusters. Out there are galaxies so vast they challenge our intuition entirely. Seedy galaxies, brightest cluster galaxies, and ultra-massive ellipticals, each one a city of light beyond comprehension. They are the heavyweights of the universe, the ones that sit at the centres of clusters, drawing in smaller galaxies like moths to a flame. Compared to them, the Milky Way is modest, balanced, almost quiet. When we look into the deep sky, we're tempted to count what we see, to make sense of the immensity by assigning it a number. It's a very human impulse, the same one that made our ancestors draw marks on bones and stones to track the days of the moon. Counting brings comfort. It puts edges on things that otherwise seem endless. But when it comes to the galaxies scattered across the universe, counting becomes an act that stretches the limits of comprehension. The numbers grow faster than the mind can follow, and before long, what you're counting is no longer just galaxies. It's time, distance, and light itself. If you stand under a truly dark sky, away from cities and noise, you might see a few thousand stars. Every one of those belongs to the Milky Way. None of them are separate galaxies. The nearest large galaxy, Andromeda, is visible as a faint smudge if you know where to look, but most of the others are far too faint to see with the naked eye. It took telescopes, long exposures, and patience to reveal that the night sky is not sprinkled with a few scattered lights, but filled with an unimaginable number of galaxies. Each small patch of sky, when magnified enough, reveals more of them, layer after layer, receding into distance until light itself begins to fade into background. When astronomers talk about the number of galaxies in the universe, they almost always mean the observable universe, the portion of space from which light has had time to reach us since the beginning of cosmic expansion. Beyond that, there may be more, but their light hasn't had time to arrive. The radius of the observable universe is about 46 billion light-years, meaning that if you could see to the farthest horizon, you'd be looking at light that has been travelling for nearly the entire 13.8 billion-year history of the cosmos. The observable universe is a sphere around us, not because we're at the centre of anything special, but because we can only see as far as light has had time to travel in every direction. Inside that enormous sphere lie perhaps 2 trillion galaxies. That number is a refinement. Earlier estimates were smaller, closer to 100 or 200 billion. As telescopes improved and we began to peer deeper into faint low-light regions, astronomers realized there were more small galaxies than anyone had imagined. Many are faint dwarfs, difficult to detect even with our most advanced instruments. Their light is dim, their stars few, but they still count as galaxies. In fact, the universe is dominated by these small, faint systems. The giant galaxies that capture our imagination are rare, scattered like bright landmarks among a crowd of smaller ones. To reach the number 2 trillion, scientists had to combine data from deep sky surveys, like those taken by the Hubble Space Telescope, with models of how galaxies evolve and how their light changes over time. What they found was that early in the universe's history, there were far more small galaxies than today. Over billions of years, many of those merged together to form larger systems, reducing the total number even as the average size increased. So, when we say there are 2 trillion galaxies, that's a count that depends on when you're asking. In the past, there were more. In the distant future, there may be fewer, as gravity continues its slow work of gathering and combining. The act of counting galaxies is in practice an act of counting light. Telescopes capture faint photons from deep space, each one travelling for millions or billions of years to reach us. The deeper we look, the older the light becomes, until we're seeing galaxies as they existed not just far away but long ago. In a single deep field image, you can see galaxies from many eras all at once, some nearby and mature, others young and irregular, still forming stars for the first time. Every point of light is a window into a different moment in cosmic history. Counting them is like counting snapshots in an album that stretches back to the beginning of time. Because light fades with distance, our ability to see faint galaxies depends on how sensitive our instruments are. The Hubble Deep Field, taken in the 1990s, revealed about 3,000 galaxies in a tiny area of sky, no wider than a grain of sand held at arm's length. Later, the Hubble Ultra Deep Field and the Hubble Extreme Deep Field pushed that number even higher. From that small sample, astronomers could estimate how many galaxies would fill the entire sky if we could look with the same sensitivity everywhere. It's an extrapolation, but a reliable one, because the universe on large scales is remarkably uniform. The same distribution of galaxies appears in every direction, a cosmic consistency that tells us the universe is the same, on average, no matter where you look. Even with that uniformity, galaxies aren't scattered randomly. They form clusters and filaments, the great cosmic web that connects everything. Counting them requires accounting for this structure, for the way they gather together in dense regions and thin out in voids. Astronomers use statistical methods to correct for these variations, building a picture of the average density of galaxies across the cosmos. That density is about 1 galaxy per 10 million cubic light years. It sounds sparse, but when you multiply that by the vastness of space, the numbers become enormous. The idea that we can even estimate this at all is a testament to the precision of modern astronomy. Each survey, each exposure, each measurement of redshift and brightness contributes to a model that tells us not just how many galaxies there are, but how they're distributed and how they've changed over time. Redshift, the stretching of light due to the expansion of the universe, allows scientists to convert light into distance. The redder the galaxy's light, the farther away it is, and therefore the older. Plotting these redshifts builds a three-dimensional map of the cosmos. Counting galaxies within that map becomes a way of counting time itself. Still, even the best counts are incomplete. Some galaxies are too faint, some too far, some hidden behind clouds of dust. The James Webb Space Telescope, with its ability to detect infrared light, has already begun to reveal galaxies that Hubble couldn't see, ancient systems from the universe's first few 100 million years. Each new observation pushes the number upward, though not in the way you might expect. Instead of simply adding more galaxies, it deepens our understanding of how the population has evolved. The early universe was packed with small, irregular galaxies, some merging to form larger ones. Over billions of years, the number of galaxies may have decreased, but the structures became grander, more complex, more luminous. If you try to imagine what 2 trillion galaxies look like, the mind quickly loses grip. Numbers that large stop behaving like quantities and start feeling like concepts. You could say there are about 7,000 stars in the observable universe, 7 sextillion, and it still wouldn't feel any more real. But perhaps there's another way to think about it. Instead of trying to hold the entire number in your head, you can think of one small piece, one patch of sky, one moment of light. Imagine pointing a telescope at a space so small it seems empty and finding it crowded with entire galaxies. Now imagine that being true for every piece of sky in every direction. That's what counting galaxies means. Not a total you can write down, but a realization that there is no emptiness anywhere you look. Galaxies, in a sense, are the pixels of the universe. Each one represents a cluster of stars, each star a potential world. When astronomers count them, they're not just tallying lights, they're measuring structure, history, and possibility. The number of galaxies tells us something about how matter has organised itself since the Big Bang, how gravity has shaped the universe into patterns of light and darkness. It also tells us about the limits of our observation. Beyond a certain distance, galaxies become so faint and redshifted that we can't see them at all. The light from those regions hasn't reached us yet. So, when we speak of 2 trillion galaxies, we're really talking about the ones inside our cosmic horizon, the ones we can observe. Beyond that, there could be more, perhaps infinitely more, scattered across space we'll never reach. The number also depends on how you define a galaxy. At one end of the scale, there are enormous systems like IC 1101, with trillions of stars. At the other, tiny dwarf galaxies barely qualify as galaxies at all, containing just a few million stars and a cloud of dark matter. Some of these dwarfs are so faint that they're difficult to distinguish from star clusters. Whether you count them as separate galaxies or not can change the total significantly. As our instruments improve, we keep finding new ones orbiting the Milky Way and Andromeda, ghostly, dim companions that remind us how incomplete even our local census is. When astronomers run simulations of the universe starting from the conditions after the Big Bang, they can watch virtual galaxies form over time. These simulations, like the Millennium or Illustris projects, show how small clumps of dark matter draw in gas, form stars, and merge to build larger structures. The simulated universes produce about the same number of galaxies as we observe, a confirmation that our understanding of physics, gravity, and cosmic expansion is roughly correct. It's a kind of cosmic bookkeeping, counting both real and simulated galaxies to see if they match. But the question of how many galaxies there are isn't just about statistics, it's also about perspective. When you realise how crowded the universe is with galaxies, the idea of our own as something special begins to shift. The Milky Way, for all its beauty, is typical. It's one of 2 trillion similar systems, each one unique in its details but built from the same ingredients. If you could somehow visit them all, you'd see familiar patterns. Spiral arms, glowing cores, clusters of stars, clouds of gas, repeated again and again like variations on a theme. That repetition doesn't make the universe less interesting. It makes it more unified. Everywhere you go, the same laws of physics shape the same kinds of light. Counting galaxies also gives us a way to measure the universe's expansion. By comparing how galaxies are distributed at different distances, astronomers can trace how far space has stretched over time. The Hubble constant, which describes that rate of expansion, was first estimated by observing galaxies' redshifts and brightness. Each new measurement refines our understanding of how the universe has grown. The galaxies are not just things to count, they're markers on the ruler of cosmic history. And yet, as precise as the measurements become, there's always an element of mystery. Beyond the reach of our telescopes, the light fades into darkness, and we can only imagine what lies farther out. Perhaps there are galaxies even larger than we know, clusters more immense than any we've detected. Perhaps the observable universe, vast as it seems, is just a tiny bubble within something far greater. Counting reminds us of what we can know, but it also hints at what we cannot. In the end, counting galaxies is a bit like counting waves on an ocean you'll never finish crossing. Each one you measure gives you a sense of the rhythm and scale, but the horizon always reveals more. The universe resists being summarized, not because it's hiding anything, but because it's genuinely too large for completion. Every new telescope, every deeper image adds detail but also complexity. The numbers may change, but the awe remains. As our journey continues, it helps to keep that perspective in mind. Our galaxy, the Milky Way, is a single point in a vast count. When we compare it to others, we're really comparing one small piece of the pattern to another. And among all those 2 trillion galaxies, some are larger, brighter, and more massive than anything we can imagine from here. They are the giants of the universe, the places where the counting stops being about how many there are and starts being about how large they can become. When you look at the night sky, every point of light seems solitary, but each belongs to a greater shape. Galaxies are not scattered haphazardly through space. They form patterns, outlines, and structures that reveal their long histories. To see a galaxy's shape is to glimpse the story of its formation. The slow pull of gravity, the collisions, the quiet spinning of matter over billions of years. The universe is full of these shapes, and although they share the same basic ingredients, stars, gas, dust, dark matter, they arrange themselves in distinct and surprisingly consistent forms. When astronomers began cataloguing the visible universe through early telescopes, they noticed that the faint, cloudy patches of light they called nebulae came in different appearances. Some were round and featureless, others elongated or spiral-like. But it wasn't until the early 20th century, after Edwin Hubble's discovery that these nebulae were actually entire galaxies, that anyone tried to classify their forms. Hubble developed a system still used today, dividing galaxies into three main categories: spirals, ellipticals, and irregulars. It's a simple framework, but within it lies the complexity of cosmic evolution. The Milky Way, our home, is a spiral galaxy, a great, flattened disk of stars rotating around a central bulge. Spirals are perhaps the most familiar type because they're visually striking. Their arms curve outward from a bright centre, filled with young blue stars, gas clouds, and dust lanes that give them a textured appearance. Some spirals, including our own, have a central bar structure running through the middle, from which the arms unwind. These are called barred spirals. The bar is made of stars and gas that funnel material toward the centre, fueling new star formation and feeding the supermassive black hole at the core. If you could look at the Milky Way from above, you'd see a pattern that resembles a giant whirlpool of light, dense near the centre, thinning toward the edges. The arms are not rigid structures but waves of density, regions where gas and stars bunch together as they orbit the galaxy. As material moves through these regions, it compresses and triggers the formation of new stars. This ongoing process gives the arms their characteristic brightness. Between the arms are darker lanes of dust and older stars, creating the contrast that makes the spiral pattern visible. Spiral galaxies like ours tend to be active. They're rich in gas and dust, the raw materials for star formation. They rotate rapidly, with stars orbiting the centre at hundreds of kilometres per second. Yet the overall structure remains remarkably stable for billions of years. This balance between motion and form is one of the universe's quiet achievements. Chaos arranged into symmetry through nothing but gravity and time. Not all galaxies have that order. The second major category, elliptical galaxies, look very different. Instead of thin disks with clear arms, they appear as smooth, rounded shapes, ovals of starlight with little structure. Their stars are older, redder, and spread in random orbits rather than organised rotation. Ellipticals range from small, nearly spherical dwarfs to gigantic systems containing trillions of stars. The largest galaxies known belong to this family. They sit at the centres of galaxy clusters, dominating their surroundings with sheer mass and brightness. Elliptical galaxies are thought to form mainly through mergers. When two spiral galaxies collide and merge, their organised rotation becomes disrupted. The gas that once formed new stars is either consumed or blown away, leaving behind a population of older stars. Over time, the merged system settles into a more rounded shape. The lack of gas means new stars form rarely, and the galaxy slowly reddens as its existing stars age. These galaxies are sometimes described as red and dead, not because they're lifeless, but because their period of star formation has ended. They're the quiet survivors of a violent past. Then there are irregular galaxies which refuse to fit neatly into either category. They have no clear shape, often appearing chaotic, as if pulled apart or frozen mid-collision. Many irregulars are small, their structures disrupted by gravitational interactions with larger galaxies. The Magellanic Clouds, two of the Milky Way's companions, are examples. They're irregular, their shapes stretched by our galaxy's gravity. Others, farther away, are irregular because they're young, still forming from clouds of gas that haven't yet settled into stable disks. Between these categories there are transitional types, lenticular galaxies for example, which have the disc-like shape of spirals but lack visible arms. They sit halfway between spirals and ellipticals, their gas depleted but their structure still intact. Lenticulars are often found in clusters where interactions with nearby galaxies strip away their gas and halt new star formation. They represent a middle stage in galactic evolution, a pause between youth and old age. Each shape tells a story not just of what the galaxy looks like now, but of what it's been through. Spirals are the children of calm environments, where collisions are rare and gas remains plentiful. Ellipticals are the products of violence, born from the merging of smaller galaxies in dense regions. Irregulars are the wanderers and the wounded, their forms disturbed by gravitational tides. Over billions of years, galaxies can move from one category to another, their shapes shifting with their circumstances. The classification system gives astronomers a language to describe what they see, but it also highlights how dynamic galaxies are. They're not static objects. They evolve. A spiral today might become an elliptical tomorrow in cosmic terms. What looks like a settled pattern is really just a moment in an ongoing process. Gravity doesn't stop shaping them, and neither does time. The shapes of galaxies also reveal clues about their contents. Spiral galaxies, with their rich supplies of gas, are bright in ultraviolet and infrared light, the signatures of young, hot stars and warm dust. Ellipticals, lacking gas, shine mainly in visible and near-infrared light, their colour dominated by older stars. Irregular galaxies can show bursts of brightness in certain regions where new stars are forming rapidly. By measuring these wavelengths, astronomers can infer not only the shape but also the age, activity and composition of a galaxy. The differences extend beyond appearance. The way galaxies move, their kinematics, reflects their shape. In spirals, stars orbit in relatively orderly paths around the centre, much like planets around a sun. In ellipticals, the motions are more random, with stars following elliptical orbits that crisscross in every direction. These patterns affect how the galaxies hold together, how they evolve, and how they interact with their surroundings. Even the dark matter halos surrounding galaxies vary with type. Spirals tend to have flattened halos that follow the disk's shape, while ellipticals have more spherical halos extending far beyond their visible edges. These halos, invisible to light but measurable through their gravitational influence, contain most of a galaxy's mass. They're what allow galaxies to remain stable despite their rotation speeds. Without dark matter, the outer stars in spirals would move too fast and fly off into space. The fact that they don't is one of the earliest pieces of evidence for dark matter's existence. When you look at photographs of distant galaxies, the diversity of their shapes is striking. Some spirals are tightly wound, their arms crisp and defined. Others are loose and open, like petals unfolding. Some ellipticals are perfectly round, others slightly flattened. Some irregulars look like faint smudges, while others blaze with newborn stars. It's a visual record of the universe's variety, each shape a result of initial conditions and subsequent history. To compare our Milky Way to these shapes is to realize how balanced it is. It's large enough to sustain steady star formation, but not so large that it's consumed by collisions. Its structure is organized but not rigid, complex but not chaotic. In the cosmic census, it sits comfortably in the middle, not among the smallest dwarfs, not among the largest giants, but just right for stability. If you were to design a galaxy meant to foster long-term habitability, the Milky Way would be a reasonable choice. Understanding galactic shapes has also helped scientists trace how the universe itself evolved. Early in cosmic history, most galaxies were small and irregular. The well-formed spirals and ellipticals we see today are products of billions of years of growth and merging. Observing distant galaxies is like looking back in time to see that transformation in progress. The irregular clumps of the early universe gradually organised into the elegant structures we recognise now. The variety of shapes we see today is a snapshot of different stages along that continuum. Galaxies don't exist in isolation. Their shapes are influenced by their environments. In crowded clusters, galaxies are constantly interacting. Their gravity distorts one another, pulling out streams of stars and gas. These tidal interactions can trigger new waves of star formation or strip galaxies of their material entirely. Spirals that fall into clusters often lose their gas to the hot plasma that fills those environments, fading into lenticulars or ellipticals. In quieter regions, like the outskirts of superclusters or the voids between them, spirals can persist for longer, their shapes preserved by relative solitude. Our galaxy's position within the local group is part of why it has kept its spiral form. We have only a few close neighbours, and though Andromeda is approaching us, the space between is vast enough that the Milky Way has had billions of years of relative calm. In the distant future, when the two finally merge, the result will likely be an elliptical galaxy, larger, rounder and redder than either of its parents. Even that eventual transformation fits the pattern observed across the universe. Spirals collide, gas ignites, stars form in bursts, and then the system settles into a quiet, smooth glow. If you could watch galaxies evolve over time, their shapes would seem to breathe. Spirals would tighten and loosen, ellipticals would expand as they merge, irregulars would twist and dissolve. The motion would be slow but continuous, like weather patterns on a planetary scale. The shapes we catalogue are only temporary expressions of ongoing processes. The universe never stops rearranging itself. The diversity of galactic shapes also hints at the universe's balance between order and entropy. Gravity creates structure, pulling matter into organised forms, but over time, interactions and collisions break down that order, leading to simpler, more diffuse configurations. In that sense, the variety of galaxies we see now represents a moment of equilibrium. Enough time has passed for complexity to emerge, but not enough for everything to fade into uniformity. The universe is old, but not yet old enough for its patterns to dissolve. And so, when we speak of the shape of starlight, we're really talking about how gravity sculpts light over time. Every spiral arm, every elliptical halo, every irregular patch of brightness is the result of matter following the simplest rule there is: masses attract. From that single principle comes everything we see: disks, spheres, arcs, filaments, and clusters. The shapes are different, but the process is the same. For all their differences, galaxies share a quiet kinship. Whether spiral, elliptical, or irregular, they all carry stars that form, live, and die. They all recycle matter. They all follow the same physical laws. Their shapes may diverge, but their essence is one. Collections of starlight bound by gravity, evolving through time. If you were drifting through space, passing from one galaxy to another, you'd see that diversity firsthand. A luminous spiral might give way to a hazy elliptical, then to a faint irregular hanging alone in the dark. Each would have its own colour, its own rhythm of light, its own quiet story. Together, they would form the grand mosaic of the universe, an endless variety built from the same few elements, arranged by the same invisible hand. And somewhere among them, one particular spiral, ours, turns slowly, patiently, carrying its small collection of stars and planets through space. From afar, it's just another patch of light, no more or less special than any other, but from within, it's everything we know. As we continue this journey outward, it becomes natural to wonder where our Milky Way fits among all these forms, how it compares not only in shape, but in scale. We've seen its spiral arms, its balanced structure, its calm environment. But how large is it really? How does it measure against others? From where we sit inside it, the Milky Way feels endless. Every direction you look, there's more light, more distance, more stars. It's easy to imagine that we live in one of the great giants of the universe simply because it feels so vast. But when astronomers compare it to the galaxies beyond, our home turns out to be something more modest, large by human standards, average by cosmic ones. It's not the brightest or the most massive, not the grandest in structure or the rarest in form. It is, in nearly every way, a middleweight galaxy, balanced between extremes, perfectly ordinary in scale, yet extraordinary in the quiet stability it provides. The numbers tell part of that story. The Milky Way spans roughly 100,000 light-years from edge to edge. That means that if you could travel at the speed of light, 300,000 kilometers every second, it would still take you 100,000 years to cross from one side of the disk to the other. From our position about 25,000 light-years from the center, we can look inward toward the dense bulge of old stars and outward toward the thinner, quieter rim. The thickness of the disk itself is only about 1,000 light-years, a slim layer compared to its width. For all its vastness, the Milky Way is an extraordinarily flat structure, a thin, rotating sheet of stars and gas turning slowly through the dark. Within that disk are between 100 and 400 billion stars. The range is wide because it's impossible to count them precisely. Many are too faint or hidden by dust. Around those stars orbit at least as many planets, probably many more. Astronomers now estimate that there are more planets than stars in the Milky Way, meaning that the galaxy might hold several hundred billion worlds. Most of them we'll never see, but the statistics are staggering. Even if only a tiny fraction are anything like Earth, that still means billions of potentially habitable worlds scattered through our spiral. The mass of the Milky Way, including its dark matter halo, is roughly 1 to 1.5 trillion times the mass of the Sun. Of that, only about 10% is invisible matter, stars, gas and dust. The rest is dark matter, unseen but inferred through its gravitational pull. This hidden mass extends far beyond the visible disk, forming a vast spherical halo that may reach 200,000 light-years in radius. It's this invisible framework that holds the galaxy together, keeping its stars from flying apart as they orbit the center. The stars in the outer regions move faster than the visible mass alone can explain. Dark matter fills the gap. In size and mass, the Milky Way is typical of large spiral galaxies. The Andromeda Galaxy, our nearest major neighbour, is somewhat larger, about 220,000 light-years across and roughly twice as massive. Many other spirals fall in the same general range. The Milky Way sits comfortably near the middle of the galactic spectrum. Smaller spirals can be only a few tens of thousands of light-years wide, with just a fraction of our star count. The largest spirals approach 200,000 or 300,000 light-years. Beyond that, the giants of the universe, the elliptical galaxies at the centres of clusters, can reach sizes of over 1 million light-years. Compared to those, our home is modest indeed. That modesty is not a weakness. In fact, it's part of why the Milky Way has endured so long. Gigantic galaxies tend to form through violent mergers that can disrupt their internal structure, heat their gas, and end their star formation. The Milky Way has avoided that kind of chaos for billions of years. It's had collisions, yes. Small dwarf galaxies have been pulled in and absorbed, leaving faint streams of stars as evidence. But it hasn't collided with another galaxy of equal size since its earliest days. That relative calm has allowed its disk to remain stable, and its spiral arms to continue producing new stars at a steady rate. Each year, the Milky Way creates the equivalent of 1 or 2 new suns worth of stars. That might not sound like much, but across billions of years it adds up to entire generations of starlight. New stars form in dense molecular clouds, hidden by dust until their radiation clears the surrounding gas and they emerge into view. Many of these nurseries lie along the spiral arms, where the density waves compress gas into the conditions needed for collapse. If you could look at our galaxy in infrared light, those arms would glow with heat from these hidden regions, tracing the slow, steady rhythm of starbirth. At the same time, old stars die, returning their material to the interstellar medium. Supernova explosions scatter heavy elements into space, enriching the gas for the next generation. This recycling keeps the galaxy chemically evolving. The Sun, for instance, formed about 4.6 billion years ago from gas already enriched by previous generations of stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all came from that long chain of stellar life and death within our galaxy. The Milky Way's modest size also affects how it interacts with its environment. It resides in a small group of galaxies rather than a dense cluster. The local group contains about 30 known members, most of them small dwarfs. Our two largest companions, the Large and Small Magellanic Clouds, orbit nearby, bound by the Milky Way's gravity. These dwarf galaxies are being slowly stripped of their gas by tidal forces, leaving behind streams that stretch across hundreds of thousands of light years. Eventually, they'll likely merge with us, adding their stars to our own. This process is part of how galaxies like ours grow, not through constant major collisions, but through a slow, steady accretion of smaller companions. The Milky Way's shape reflects that ongoing evolution. It's not perfectly symmetrical. The disk is slightly warped, likely due to gravitational interactions with the Magellanic Clouds or with the dark matter halo itself. One side of the disk bends upward, the other downward, creating a gentle curve when viewed from outside. These distortions remind us that even in apparent calm, our galaxy is not static. It flexes, it vibrates, it breathes in its own slow way. Our spiral arms are another sign of dynamic balance. The Milky Way has 4 major arms: Perseus, Scutum Centaurus, Norma, and Sagittarius Carina, as well as smaller spurs connecting them. The Sun lies in one of these spurs, the Orion arm, a minor feature between 2 larger arms. From this quiet location, about halfway between the centre and the edge, we orbit the galaxy every 230 million years. In that time, the solar system travels about 800,000 kilometers per hour, yet from our perspective, the stars seem fixed, because the distances are so immense. Everything moves together, slowly and steadily, as if frozen in time. Looking inward from our position, the galactic centre lies in the direction of the constellation Sagittarius. It's home to Sagittarius A, the supermassive black hole that anchors the galaxy. Surrounding it are dense clusters of stars and swirling clouds of gas. Although we can't see the black hole directly, radio and infrared observations reveal stars whipping around it at extraordinary speeds. From their motion, astronomers can measure its mass precisely, about 4 million suns. Despite its power, it's relatively quiet compared to the active black holes at the centres of some other galaxies. It's not currently feeding heavily, only a small trickle of material falls in. For now, it rests, and our galaxy with it. The outer regions of the Milky Way are more diffuse. Beyond the visible disk lies a halo of old stars and globular clusters, spherical collections of hundreds of thousands of stars bound tightly together. These clusters orbit far above and below the disk, relics of the galaxy's earliest epochs. Many are more than 10 billion years old, nearly as ancient as the universe itself. They're fossils of the Milky Way's formation, remnants of the smaller systems that merged to build it. Compared to the giants of the universe, the Milky Way's modesty is also apparent in its luminosity. It shines with the light of about 10 billion suns. That might seem overwhelming, but the largest galaxies can radiate 10 times that amount. In visible light, the Milky Way's brightness is typical of a Monsieur spiral, not faint, not dazzling, but balanced. Its colour is a soft white with a slight yellow tint. the result of the mixture of young blue stars and older red ones. From afar, it would look like a glowing disk of pale light against the black. That balance between youth and age, activity and calm, makes the Milky Way a kind of archetype, the galaxy you might imagine when you picture a spiral. It's the average against which others are measured, and yet even within that ordinariness, there are subtle distinctions that make it unique. Its bar structure is stronger than some, weaker than others. Its rotation curve provides important evidence for dark matter. Its satellite system offers clues to how galaxies grow. Every typical galaxy still has its quirks. In the grand context of the universe, our Milky Way is neither among the first nor the last of its kind. Galaxies began forming about 13 billion years ago, and they will continue to exist for billions more. We live at a midpoint in cosmic history, when the universe still produces new stars but has already matured enough for complex structures to form. The Milky Way reflects that balance, old enough to be stable, young enough to remain active. There's something quietly reassuring about that. In a universe of extremes, massive ellipticals blazing in clusters, tiny dwarfs flickering in the void, our galaxy sits comfortably in between. Its modesty allows for longevity. Its calm environment allows for life. The same conditions that make it average in cosmic terms make it exceptional for us. When astronomers compare galaxies statistically, they often find that the Milky Way's properties align closely with the median. In star formation rate, mass, and luminosity, it falls right near the middle. The Andromeda galaxy is slightly larger and more massive, and the Triangulum galaxy, another member of our local group, is smaller. Together, the three form a miniature hierarchy within our region of space. Beyond that, the Virgo cluster, some 50 million light-years away, contains galaxies of every type, including some that dwarf all three. It's in clusters like that where the true giants live. But before we reach those giants, it's worth lingering on what our galaxy represents. The Milky Way's modest size is not a limitation. It's a sweet spot in cosmic design. Large enough to sustain star formation for billions of years, small enough to remain stable, isolated enough to avoid constant collisions, and rich enough to build the complex chemistry needed for planets and life. If galaxies could be ranked by habitability rather than size, the Milky Way would be among the finest environments in existence. To understand that better, imagine scaling galaxies to human proportions. If the largest elliptical galaxies were sprawling metropolises, filled with light and noise, our Milky Way would be a mid-sized city, not small, not provincial, but livable, balanced, full of quiet neighbourhoods and long avenues of stars. Within it are countless solar systems like houses, each with its own story, its own chemistry, its own history. From that perspective, the Milky Way's modesty becomes a kind of grace. It's big enough to contain wonders, but small enough to feel familiar. Its scale is still staggering when measured in human terms. The light that left the far side of the disk when early humans were learning to control fire is only reaching us now. The nearest major galaxy, Andromeda, though it looks close in images, is 2.5 million light-years away. The faintest dwarfs orbiting us are hundreds of thousands of light-years distant. Yet all of that fits within the framework of a single galaxy, our modest spiral. When you see it written out as a number, 100,000 light-years, it's just digits. But when you imagine it as distance, it's a span beyond comprehension. And still, among the billions of galaxies beyond, it's an average. The universe is full of spirals like ours, some smaller, some larger, all turning slowly through the same dark sea. Ours happens to be the one we inhabit, the one whose stars gave us the atoms in our bodies, the one whose balance of scale and calm made it possible for life to appear on a small blue planet near one of its middle arms. It's modest, yes, but perfectly suited to host beings capable of wondering what modesty even means in cosmic terms. When we talk about our galaxy, It's easy to think of it as a single, self-contained island drifting in space, but no galaxy truly moves alone. They gather, like families, drawn together by gravity into groups and clusters that drift through the universe as one. Our own Milky Way belongs to one of these small cosmic families, the local group. It's not large as galaxy clusters go, but it's home to our spiral, its luminous neighbour Andromeda, and dozens of smaller companions orbiting quietly around them. Together they form a small, loosely bound cluster, moving gently through the darkness. The local group spans about 10 million light-years across. It's a region of space where the pull of gravity between its members outweighs the expansion of the universe. Outside of that boundary, space itself stretches fast enough that galaxies drift apart forever. Inside it, gravity wins. The galaxies of the local group orbit their shared centre of mass, interacting slowly, subtly, on timescales that make even the ages of stars seem brief. It's a system in motion, though its rhythm is so slow that it feels almost still. At the heart of this quiet cluster are two great spirals, our Milky Way and the Andromeda Galaxy, also known as M31. They're the two largest members by far, each with a halo of smaller galaxies circling around them. The Milky Way sits near one edge of the group, Andromeda near the other. Between them lies a gulf of 2.5 million light-years, vast but not unbridgeable in cosmic terms. The gravitational pull between them is enough that they are slowly drawing closer. In about 4 billion years they'll meet, merging into a single, larger galaxy. For now they glide toward each other at about 110 kilometers per second, fast by human standards, slow by cosmic ones. Between these two giants lies a third notable spiral, smaller but significant. The Triangulum Galaxy, or M33. It's about 60,000 light-years across, roughly half the size of the Milky Way, and may orbit around Andromeda as a smaller companion. The Triangulum is rich in star-forming regions, glowing with clusters of young blue stars and pink clouds of ionized hydrogen. It's the third largest member of the local group, and though it's much smaller than its two neighbours, it provides a link between them, a kind of bridge of light and gravity. Around these three major spirals orbit a collection of smaller galaxies, most of them dwarfs. The Milky Way alone has more than 50 known satellites, though new ones are still being discovered as telescopes grow more sensitive. Some of these dwarfs are bright enough to be seen with small instruments, the Large and Small Magellanic Clouds, for example, visible from the southern hemisphere as faint, misty patches near the Milky Way's edge. Others are so faint that they were only found in the past 2 decades, their light barely distinguishable from the background sky. The Large Magellanic Cloud, or LMC, is the largest of these companions, spanning about 14,000 light-years. It's an irregular galaxy, distorted by our gravity and by its own smaller partner, the Small Magellanic Cloud, or SMC. Together they orbit the Milky Way, trailing long streams of gas known as the Magellanic Stream. This stream stretches across the sky, hundreds of thousands of light-years long, wrapping around the Milky Way like a faint ribbon. It's made of hydrogen pulled from the clouds by tidal forces. Eventually, this material will fall into our galaxy, feeding new star formation, a quiet act of galactic recycling that has been happening for billions of years. Beyond these bright companions lie numerous dwarf spheroidal galaxies, small, faint, and diffuse, containing only a few million stars each. The Sculptor, Fornax, Draco, and Ursa Minor dwarfs are examples. They orbit far from the Milky Way's disk, like scattered embers around a campfire slowly circling the main mass. Most of them are dominated by dark matter, their visible stars just a trace of their total content. They're fragile things, easily disrupted by tidal forces. Some are already being torn apart, leaving behind streams of stars that stretch through our halo. The Sagittarius dwarf galaxy, for instance, is currently in the process of merging with us, its stars forming long arcs across the sky. Andromeda has its own collection of satellites. More than 30 are known. Among them are the bright dwarf ellipticals M32 and M110, which lie close enough to be seen in the same field of view as Andromeda itself. M32 is compact and dense, perhaps the stripped core of a larger galaxy consumed long ago. M110 is more diffuse, a faint oval of older stars. Around Andromeda, as around the Milky Way, many smaller galaxies orbit in long, slow loops, each one a remnant of the local group's gradual assembly. Between these galaxies stretches the intergalactic medium, the faint gas that fills the space between systems. It's not empty, though it's thinner than the best vacuum we can make on Earth. A few atoms per cubic meter drift through that space, along with invisible filaments of dark matter that bind the group together. These filaments connect the Milky Way, Andromeda, and their satellites into a single gravitational system. The entire local group is moving as one body through space, heading slowly toward the Virgo cluster, the nearest large cluster of galaxies about 50 million light-years away. In diagrams, the local group often looks like a scatter of dots, each one a galaxy, each labelled by name and distance. But in reality, it's a delicate three-dimensional dance, every member in motion, every orbit affected by the pull of its neighbours. The Milky Way and Andromeda are the main dancers, their steps set on a collision course billions of years from now. The smaller galaxies move around them, their paths tracing loops that will one day merge into the larger system that results. It's difficult to picture this dance in real time because it unfolds so slowly. On human timescales, the local group seems frozen, but if you could speed it up by a factor of 1 billion, you'd see the galaxies weaving and circling, their orbits curving through space. The dwarfs would approach, stretch, and dissolve. The spirals would twist and tilt. The Milky Way and Andromeda would close the gap between them, their halos overlapping long before their disks touch. The final collision will take hundreds of millions of years, but its outcome is already written in the motion of the stars. When the two great spirals meet, their shapes will distort. Tidal forces will pull out long streams of stars, forming arcs that bridge the space between them. Clouds of gas will collide, igniting bursts of new star formation. The central black holes will spiral together and eventually merge, releasing immense energy. Over time, the two galaxies will settle into a single, larger elliptical galaxy, sometimes nicknamed Milkomeda. The orderly spiral arms will vanish, replaced by a smooth, featureless glow. The new galaxy will still contain the same stars, including our Sun, if it still exists, but they'll orbit in new patterns, their ordered motion turned random by the merger. This kind of collision isn't rare, it's part of how galaxies grow. The local group today is just a snapshot of one stage in that process. In the distant past, there were likely more small members, many of which have already merged with the larger ones. In the future, there will be fewer as the remaining dwarfs are absorbed. Gravity is patient, it never stops. The local group is slowly evolving toward unity. Even now, faint evidence of past mergers is visible in the halos of both the Milky Way and Andromeda. Streams of stars, too faint to see with the naked eye, arc across the sky, remnants of long-consumed dwarfs. The Gaia spacecraft has mapped some of these structures in exquisite detail, revealing that much of the Milky Way's outer halo was built from smaller galaxies that fell in long ago. Their stars still carry distinct chemical fingerprints, clues to their origins. It's a reminder that galaxies, like people, carry the traces of everything they have encountered. The local group's small size makes it easier to study in detail. Every one of its members has been mapped, measured, and modelled. The distances between them are known, the motions tracked. It's a laboratory for understanding how galaxies form and evolve. The relationships between its members mirror the relationships in larger clusters, just on a smaller scale. The same physics applies: gravity, dark matter, the flow of gas, the slow exchange of stars. If you were to stand at the edge of the Milky Way's halo and look outward, Andromeda would dominate your view, a disk of light stretching several times wider than the full moon, though too faint to see without magnification. Its spiral arms would be visible as faint swirls, its bright nucleus glowing with the combined light of hundreds of billions of stars. You'd see its satellites clustered around it like fireflies. Between the two galaxies, the space would appear empty, but gravity would be at work, drawing them together imperceptibly. Farther out, the Triangulum galaxy would shine smaller and dimmer, and beyond that, the dwarfs of the local group would appear as tiny smudges scattered across blackness. If you could look farther still, you'd see the faint outline of the Virgo cluster, its countless galaxies blending into a soft haze. The local group drifts toward that cluster, but it will never join it. The expansion of the universe will carry it away faster than gravity can pull it in. Eventually, billions of years from now, the local group will become an isolated island in the expanding cosmos, surrounded by darkness, its remaining galaxies merged into one. For now, though, the local group remains an interconnected family. Each galaxy exerts its pull on the others, but the motions are slow and steady. It's a system in equilibrium, a cosmic neighbourhood where nothing happens quickly and nothing ever truly stops. The Milky Way's satellites circle quietly. Andromeda's companions trace their paths. The Triangulum drifts nearby, perhaps orbiting, perhaps just passing through. It's a kind of galactic choreography, patient and balanced. There's a comfort in realizing that our galaxy isn't alone, that it moves through space in company. The distances between the local group's members are enormous, but the gravitational bonds between them are real. Even in the emptiness between galaxies, there is connection, invisible, constant, enduring. The light of one system influences the structure of another. The pull of one shapes the path of the next. The whole group moves together through the dark, a small gathering of light in an infinite sea. And somewhere within one of those spirals, on a small planet orbiting an ordinary star, we have the chance to look outward and notice all of this, to measure, to imagine, to understand. We're part of the dance, though our steps are too small to see. As our gaze drifts beyond the local group, the scale widens again. The small cluster that holds our galaxy and its neighbours is just one of many such groups scattered through the nearby universe. Beyond lies the Virgo cluster, larger, denser, filled with thousands of galaxies, and among them are the true giants, the galaxies that dwarf everything in our neighbourhood. The quiet balance of our local group gives way to crowded arenas where gravity pulls with greater force and where galaxies collide not gently over billions of years, but violently and often. Among the many companions of our Milky Way, one stands apart. Not a faint dwarf drifting nearby, not a satellite orbiting quietly at the edge of our halo, but a true equal, perhaps even a rival. The Andromeda galaxy, known to astronomers as M31, is the nearest large spiral to our own, a neighbour in both distance and destiny. When we speak of the local group's future, we are really speaking about the story between these two galaxies, twin spirals caught in a long, slow gravitational embrace that will eventually draw them together. If you could look toward the constellation Andromeda on a clear moonless night, you could see it without any telescope at all. It appears as a faint, elongated smudge of light, barely perceptible to the naked eye. That hazy patch is the glow of 1 trillion stars, their combined light travelling for 2.5 million years to reach us. When that light first left Andromeda, early humans had not yet walked the Earth. Entire epochs have passed since then, yet the light still arrives, unhurried, carrying the distant reflection of a galaxy that, in many ways, mirrors our own. In structure, Andromeda is a spiral galaxy similar to the Milky Way, but larger and more massive. Its diameter extends about 220,000 light-years, more than twice the width of our galaxy's stellar disk. Its mass, including its dark matter halo, is estimated at around 1.5 to 2 trillion solar masses. The exact figure is uncertain, but most studies place it just ahead of the Milky Way. It contains roughly 1 trillion stars, perhaps 3 times as many as our galaxy, and shines with the light of 10 billion suns. When viewed through telescopes, Andromeda's disk appears tilted, allowing us to see its structure clearly. Broad spiral arms sweep outward from a bright central bulge, laced with dark dust lanes that trace the pattern of interstellar gas. Its core glows intensely, the light of billions of tightly packed stars surrounding a central black hole. Around the main disk, faint streams of stars arc outward, the remnants of smaller galaxies absorbed in the past. These tidal features tell a story of growth through mergers, of a galaxy that has built itself from the gradual consumption of others. The Milky Way and Andromeda are similar in more than just appearance. Both are barred spirals, both host supermassive black holes at their centres, and both are still forming stars. But there are differences in their personalities, if a galaxy can be said to have one. Andromeda is more luminous, with a slightly faster rotation speed and a higher rate of stellar formation. Its central region is more complex, containing a double nucleus, 2 clusters of stars orbiting a shared centre, likely the result of a past merger. Its halo is larger and denser, filled with the debris of disrupted dwarfs. In a way, Andromeda feels older, more evolved, as though it's a glimpse of what the Milky Way might look like a few billion years from now. The space between our 2 galaxies, though vast, is not empty. It's filled with tenuous gas and the faint threads of dark matter that connect them. Their halos already overlap, though the visible disks are still far apart. The gravitational attraction between them is enough to overcome the expansion of the universe at this distance. Slowly, imperceptibly, they are moving toward each other at about 110 kilometers per second. Over the course of billions of years, that steady approach will end in collision. Astronomers can predict this future with surprising precision. Using data from the Hubble Space Telescope and the Gaia mission, they've measured the motions of Andromeda's stars and determined its trajectory. The first close approach will happen in about 4 billion years. When that time comes, the 2 galaxies will pass through one another, their stars flying by mostly unharmed, since the distances between stars are immense. But the gravitational tides will distort both disks, pulling out long tails of stars and gas. Over the next few billion years, the galaxies will swing past each other several times, each encounter drawing them closer until they finally merge into a single, larger system. That future galaxy will likely be an elliptical, its spiral arms erased by the collision. The orderly rotation of stars will give way to random orbits. The gas will be consumed or expelled, and star formation will gradually fade. The supermassive black holes at the centres of the Milky Way and Andromeda will spiral toward each other, losing energy through gravitational waves until they merge into one. For a brief moment, the universe will tremble with the energy of that event, then settle again. The new galaxy, sometimes nicknamed Milkomeda, will shine as a giant elliptical, bright and stable, containing the combined stars of both predecessors. If life still exists in our galaxy by then, the view of the sky will change in spectacular ways. Long before the final merger, Andromeda will grow larger in the night sky, transforming from a faint smudge to a glowing disk that dominates the heavens. Its spiral arms will become visible to the naked eye, stretching across the stars. As the galaxies approach, streams of light will arch between them, forming bridges of stars. The Milky Way's familiar band will distort, its symmetry broken by the gravitational pull. For hundreds of millions of years, the night will glow with double spirals, 2 galaxies entwined in slow motion. But despite the drama of such a collision, it's not a destructive event in the way we might imagine. Stars are so far apart that direct impacts are virtually non-existent. Even as the galaxies pass through each other, most stars simply move along new paths. What changes are the orbits, the structure, and the gas. The interstellar clouds will collide, compressing and igniting bursts of new star formation. The sky will fill with clusters of young blue stars shining in the aftermath of those encounters. The merger will be violent in scale but graceful in effect, a transformation rather than a catastrophe. The relationship between the Milky Way and Andromeda is one of cosmic inevitability. Gravity binds them. Time ensures their meeting. For now, they are two great spirals turning in parallel, their light crossing the void between them. Each year, the distance between shrinks by about 100 kilometers per second. Over human history, that's barely a fraction of a light year, but in cosmic terms, it's an unbroken motion that has continued for billions of years. Their connection extends beyond mere motion. Studies of the gas and stars in their halos suggest that the Milky Way and Andromeda may have interacted before. Not a collision, but a close passage in the distant past, perhaps 10 billion years ago, when the universe was still young. If that's true, then the two galaxies have been linked for most of cosmic history, orbiting each other in a slow gravitational dance that will end only when they become one. Andromeda's halo is one of its most striking features. Extending over 1 million light-years, it contains vast amounts of hot gas and old stars. Observations by the Hubble Space Telescope have shown that this halo is roughly as massive as the visible galaxy itself. It's so large that if it were visible to the naked eye, it would stretch across an area of the sky many times wider than the full moon. The halos of Andromeda and the Milky Way already intersect, meaning that, in a sense, the merger has begun at the outermost edges. The galaxies are not yet touching in their luminous parts, but their invisible atmospheres are mingling, sharing gas and dust. Andromeda also hosts its own collection of satellite galaxies, much like the Milky Way. The two most prominent, M32 and M110, lie close to its disk, easily visible in long exposure images. M32 is a compact elliptical, dense and bright, possibly the stripped core of a larger galaxy devoured by Andromeda long ago. M110 is more diffuse, with a faint extended halo of stars. Beyond these, many smaller dwarfs orbit farther out, each following its own path through the halo. Their motions reveal the structure of Andromeda's gravitational field, giving astronomers clues about the distribution of its dark matter. In total, Andromeda's system, the galaxy, its satellites, and its halo, spans well over 1 million light-years. It dominates its half of the local group, much as the Milky Way dominates ours. The two systems together form a binary pair, the gravitational centre of our local cluster. Everything else, the dwarfs, the Magellanic Clouds, the Triangulum Galaxy, orbits around the combined mass of these two giants. When we observe Andromeda, we're looking not just at a nearby galaxy, but at a preview of our own future. Its slightly greater mass and older structure suggest it may be ahead of us in its evolution. The streams of stars in its halo are signs of mergers already completed, hints of the same fate that awaits our Milky Way when it absorbs its smaller companions. The faint reddish colour of its bulge, the widespread population of old stars, and the subdued rate of star formation all point to a galaxy that's maturing, transitioning slowly toward the quieter phase that all spirals eventually reach. For astronomers, Andromeda has long been a cornerstone of galactic research. Because it's so close, it serves as a benchmark for studying distant systems. Its stars can be resolved individually, its rotation measured directly, its distance determined with precision. It was in Andromeda that Edwin Hubble first identified Cepheid variable stars, leading to the discovery that galaxies lay far beyond the Milky Way, proof that the universe was far larger than previously imagined. To this day, Andromeda remains a kind of laboratory for understanding how galaxies work. Its proximity also makes it a source of perspective. When you look at Andromeda through a telescope, you're seeing a galaxy very much like our own from the outside. It's the closest thing we have to a mirror view of the Milky Way. Every swirl of light, Every dust lane, every cluster of stars could have its counterpart here. It's both familiar and alien, a reflection of home seen across the gulf of space. If you imagine standing within Andromeda, on one of its countless worlds, looking outward into the dark, the Milky Way would appear much the same. A faint band of light stretching across the sky, another spiral glowing in the distance. The beings there, if any exist, might look toward us and wonder about our stars, just as we wonder about theirs. Two galaxies, two homes, separated by time and distance, linked by the same gravity and the same curiosity. The Andromeda Galaxy reminds us that scale is relative. From Earth it seems impossibly far, a misty smear of light beyond reach. But from the perspective of the universe, it's next door. In a cosmos 93 billion light-years across, 2.5 million is hardly any distance at all. The light that connects us has travelled longer than the span of human civilization, yet compared to the age of the universe, that's only a moment. When you think of Andromeda that way, not as a distant object but as a companion, the idea of the local group becomes less abstract. We live in a small pocket of space where two great spirals turn side by side, their satellites circling, their halos intertwined. It's a neighbourhood, vast beyond comprehension, yet intimate in its structure, and in time, that neighbourhood will condense into one great luminous city of stars. Beyond the local group lie clusters where galaxies are packed far more tightly, where hundreds or thousands coexist within a few million light-years, where collisions happen often and the giants grow even larger. Compared to those, our relationship with Andromeda is quiet, a long prelude to a slow union. The true behemoths live out there, in the centres of those clusters, their light stretching across the universe. The idea of galaxies colliding can sound violent, like two solid objects crashing together in space, scattering debris and light. But galaxies are not solid, and the spaces between their stars are immense. When they meet, they pass through each other more like clouds than stones, their stars slipping by unharmed. What changes is their structure, the graceful order of spiral arms, the calm orbit of stars, the quiet balance of gas and dust. Gravity reaches across the distances, stretching and distorting, rearranging everything in slow motion. What we call a collision is really a transformation, a long sequence of encounters that can take billions of years from beginning to end. If you could watch a galactic collision unfold on fast forward, what you'd see would not be destruction but choreography. Two great disks of light approach, their halos overlapping first. The faint outer stars begin to feel each other's pull, their orbits shifting slightly. Then, as the cores draw closer, tidal forces rise, arms twist, streams of stars arc outward, forming long, delicate bridges between the galaxies. Their shapes stretch and bend, their symmetry unravels. Clouds of gas within them collide directly, compressing into bursts of new stars that flare briefly, like sparks in the dark. Then the galaxies pass through one another, moving apart again, their forms changed. After millions of years, they slow, turn back and fall together once more. Each encounter leaves them more entangled, until finally, after several passes, they merge completely, settling into a new, larger galaxy. This process, as dramatic as it sounds, is one of the fundamental mechanisms of cosmic evolution. Galaxies grow through mergers. From the smallest dwarfs to the largest giants, every one of them has absorbed others at some point in its history. Even our Milky Way bears the scars of past collisions, faint streams of stars in its halo, remnants of smaller galaxies it has consumed. The local group itself is the product of such interactions. Andromeda has swallowed many smaller companions. The Milky Way is doing the same right now. These events are so common that they shape the very population of galaxies we see across the universe. When two galaxies collide, the first thing that changes is the motion of their stars. Before the encounter, most stars follow orderly orbits around their galaxy's centre. As the two systems draw near, their gravitational fields overlap, and those orbits become chaotic. Some stars are flung outward into long tails, while others fall inward toward the centre. The overall energy of the system redistributes, converting organised rotation into random motion. Over time, this process erases the distinctive disk structure of spiral galaxies. The end result is usually an elliptical galaxy, a smooth, featureless ball of stars with a little rotation and little gas. The gas itself behaves differently from the stars. While stars mostly pass by one another, gas clouds actually collide. When they do, they compress, heating up and triggering intense bursts of star formation. These starbursts can create tens or hundreds of new suns per year, far more than the quiet pace of a typical spiral galaxy. The light from these newborn clusters can make merging galaxies some of the brightest objects in the sky. For a brief period, perhaps a few 100 million years, they shine fiercely, then gradually fade as the gas is consumed or expelled by winds from massive stars and supernovae. The antennae galaxies, about 60 million light-years away in the constellation Corvus, are one of the best-known examples. Two spiral galaxies, roughly the size of the Milky Way, are in the midst of merging. Long tidal tails extend outward from their centres, resembling the delicate antennae of an insect. In their overlapping region, clouds of gas are colliding, igniting vast clusters of new stars. Infrared images show hundreds of bright knots where stars are forming at incredible rates. In a few 100 million years, the two will have merged completely, becoming a single, more rounded galaxy. Another striking example is the Whirlpool galaxy M51, interacting with its smaller companion NGC 5195. The smaller galaxy has passed through the larger's disk, triggering waves of density that have sharpened the Whirlpool's spiral arms and fueled bursts of star formation along them. From our vantage point, it's a nearly perfect face-on spiral, with one arm visibly distorted by the gravitational pull of its partner. This kind of encounter shows that collisions don't always destroy spirals. Sometimes they enhance their structure, adding drama and detail before the eventual merger. Farther away, in the realm of massive clusters, collisions happen on a much grander scale. There, galaxies move at thousands of kilometers per second, and the density of systems is far higher. When they meet, the results are spectacular. Some of the brightest radio galaxies, those that emit enormous jets of energy from their central black holes, are found in these dense environments, often the aftermath of recent mergers. The collisions funnel gas toward the centre, feeding the black hole and triggering outbursts that can extend for millions of light years. The centres of galaxy clusters are often occupied by these giants, enormous ellipticals that have grown by consuming others. Each merger adds new stars to their halos, new material to their cores, and new energy to their dynamics. Over billions of years, repeated collisions turn once distinct galaxies into single, massive structures that can contain trillions of stars. The process is slow but relentless. Gravity has no end and no exhaustion. Even though galaxies collide often, the risk to individual solar systems is minimal. The distances between stars are so large that direct stellar collisions are virtually impossible. The Sun, for example, will likely survive the future Milky Way Andromeda merger intact, though its orbit will change. After the merger, our solar system may find itself flung to a new position within the combined galaxy, perhaps farther from the centre, perhaps closer. The night sky would transform, filled with new patterns of stars, but the Sun would remain, still shining, still stable. The Earth, if it still exists, would orbit quietly amid the shifting sea of light. Galactic collisions also play an essential role in spreading the elements necessary for planets and life. When gas clouds crash and stars are born in the chaos, supernova soon follow. Those explosions enrich the interstellar medium with heavy elements: carbon, oxygen, nitrogen, iron, which then become part of new generations of stars and planets. In that sense, collisions are engines of cosmic renewal. They redistribute material, mix it, and restart cycles of creation that might otherwise fade. The shapes that result from these encounters are some of the most beautiful and complex in the universe. The tadpole galaxy, for instance, stretches out a tail nearly 300,000 light-years long, formed by stars pulled away during a collision. The mice galaxies, another interacting pair, show twin trails curving outward, the result of their gravitational dance. Each shape is unique, a frozen moment in a process that lasts hundreds of millions of years. Astronomers study these systems to understand the mechanics of gravity on vast scales, how tides, momentum, and energy combine to reshape entire galaxies. Computer simulations now allow scientists to recreate these events in detail. By modelling the masses, velocities, and gas content of two galaxies, they can watch how the interaction unfolds. The results often match what we see in real images, confirming our understanding of the physics. The first encounter stretches the disks, forming tidal tails. The second brings the cores closer. The final merger erases the disks, leaving behind an elliptical remnant. Each stage has its own beauty, its own rhythm, its own sense of inevitability. Our future merger with Andromeda will likely follow this same pattern. The first close pass will distort both galaxies, triggering waves of star formation. The second encounter will bring them together, their black holes beginning their slow inward spiral. After several billion years, they will become one, a new larger galaxy glowing quietly in the dark. Astronomers predict that the final system will be an elliptical several 100,000 light-years across, containing perhaps twice the number of stars of either original. The local group, once a collection of many members, will by then have coalesced into this single object, drifting through the expanding universe. In the far future, when cosmic expansion has carried other galaxies beyond our observable horizon, this merged system may be all that remains visible from within. The night sky of that distant epoch will contain only the stars of our own galaxy. The rest of the universe will have faded from view, carried away faster than light by the acceleration of space. The merger we await will not just reshape our local environment, it will define the cosmic landscape of the future. Yet even that final state is only temporary. Over trillions of years, star formation will cease as the gas runs out. The remaining stars will burn their fuel and fade into darkness. The black hole at the centre will continue to grow as it absorbs what little remains. Eventually the galaxy will dim, its light dispersing, its energy spent. What began as a bright collision of two spirals will end as a quiet, dark remnant drifting through the void. Every galaxy shares that fate, though it lies far beyond any time we can imagine. Still, in the present, collisions are signs of life, of movement, of change. They show that the universe is not static. Every time two galaxies meet, the cosmos becomes more complex. New stars ignite, new structures form, new patterns emerge. The universe breathes through these encounters, expanding and evolving in ways that are both vast and delicate. When astronomers look out across the observable universe, they see collisions in every direction. In deep-field images, some galaxies appear warped or doubled, their shapes twisted by recent interactions. Others show long tails or faint bridges connecting them to neighbours. Some have ring-like structures formed when smaller galaxies plunge through their disks. These are snapshots of a dynamic universe, frozen moments in stories that will continue for billions of years after the light reaches us. It's easy to think of collisions as rare, given the vastness of space, but in galactic terms, they're inevitable. Gravity ensures that no system stays isolated forever. Over time, small groups merge into larger ones, clusters combine into superclusters, and galaxies themselves coalesce into ever bigger structures. The universe began with uniformity, a nearly smooth sea of gas, and has spent its history forming clumps, building complexity through the simple rule of attraction. Collisions are the natural outcome of that process. And though we often imagine these encounters as destructive, the reality is that they are also creative. Without them, galaxies would remain smaller, their gas unspent, their stars fewer. The variety we see, the range of shapes, sizes and colours, is the result of billions of collisions over cosmic time. Even the largest ellipticals, serene and featureless today, were once spirals that collided and merged in the distant past. The smoothness of their light is the calm after the storm. If you could see a time-lapse of the universe from beginning to end, galaxies would flicker and merge like droplets on a window pane. Small ones would cluster, combine and grow. Spirals would twist into ellipticals. Streams of stars would stretch and fade. The scale would be beyond comprehension, yet the motion would have a kind of grace. The quiet unfolding of gravity's work across billions of years. And in that motion, there's something profoundly steady. Despite the chaos, the universe follows its rules perfectly. Every merger, every distorted spiral, every luminous bridge of stars happens exactly as physics predicts. There's no randomness in the overall design, just the slow transformation of matter guided by gravity, time and energy. The galaxies collide, but the laws that govern them never change. When we move beyond the familiar spirals of our local group, we start to encounter galaxies that defy easy comparison. The scale we've grown accustomed to, 100,000 light-years across, a few 100 billion stars, a calm disk turning slowly through space, begins to seem small. Out in the deep clusters of the universe live galaxies so enormous that they stretch the limits of what gravity can hold together. They are the giants of creation. The colossal kind, sitting at the centres of galaxy clusters like glowing hearts, surrounded by smaller companions. Everything around them orbits their light. These massive systems, often called giant ellipticals or brightest cluster galaxies, are among the most impressive structures the universe has produced. The largest of them can span over 1 million light-years, 10 times the width of the Milky Way. Their masses can exceed 10 trillion suns, containing hundreds of times as many stars as our own galaxy. From a distance they appear as smooth, oval glows, their light fading gradually into the dark. There are no visible arms, no bands of dust, no clear boundaries. They're more like luminous clouds than objects, their stars moving in random orbits that blur into one another. Unlike spirals, which form gradually from rotating disks of gas, these giants are built through the repeated merging of smaller galaxies. In the dense centres of clusters, where hundreds or thousands of galaxies crowd together, collisions are inevitable. Each encounter adds more stars, more gas, and more mass to the central system. Over billions of years, the cluster's smaller members are absorbed, their light joining the collective glow. The result is a single immense galaxy, surrounded by faint traces of its past, streams and shells of stars left behind by the galaxies it consumed. One of the most famous of these is IC 1101, located in the Abell 2029 cluster, about 1 billion light-years away. It is, by most measurements, one of the largest known galaxies in the observable universe. Its diameter is estimated at around 6 million light-years, and it contains roughly 100 trillion stars. That number is difficult to grasp. Even if you could count one star every second without stopping, it would take more than 3 million years to finish. And yet, all of them exist within this single, luminous structure, orbiting quietly in the darkness. The light from IC 1101 is old. What we see today left that galaxy when life on Earth consisted of little more than simple, multicellular organisms in the oceans. Since then, our world has changed entirely, while that light has continued its journey across space, carrying with it the silent record of a civilization of stars too vast to imagine. If you could see it up close, it would not look like a flat disk, but a vast, diffuse sphere. The outer regions so faint that they blend into the background sky. Its core, however, would blaze with the combined glow of countless suns packed into a volume thousands of light years wide. The stars in such galaxies move not in circles, but in every direction at once. There is no single axis of rotation, no ordered disk. Each star follows its own path through the gravitational field of the whole, weaving through the others without collision. The result is a kind of dynamic equilibrium, random motion creating stability. The same principle holds true for all large ellipticals. Their stars form a swarm rather than a pattern, 1,000,000 billion suns held together by their collective gravity. At the centres of these giants lie supermassive black holes, much larger than those in ordinary galaxies. The black hole at the core of IC1101 is estimated to contain tens of billions of solar masses. When gas falls toward it, the energy released can outshine the entire galaxy, producing what astronomers call an active galactic nucleus, or quasar. In its younger days, IC1101 may have blazed as one of these brilliant objects, its black hole feeding greedily on infalling matter. Today, it has quieted, its fuel mostly consumed, leaving only a faint X-ray glow where once there was a beacon visible across the universe. Other massive galaxies tell similar stories. In the Coma cluster, about 320 million light-years away, two giants dominate the centre, NGC 4874 and NGC 418. Each is several 100,000 light-years wide and contains trillions of stars. Their mutual gravity holds the cluster together, and their halos overlap, filling the central region with diffuse starlight. Between them drift hundreds of smaller galaxies, the remnants of earlier mergers. The Coma cluster is a city of galaxies, and these two are its central towers, built from the accumulation of everything that came before. In clusters like these, the boundaries between galaxies blur. The space between the largest systems is filled with a faint diffuse glow called intracluster light. Stars that have been stripped from their homes during collisions and now orbit freely within the cluster's gravitational field. This ghostly light is difficult to see, but it's there, wrapping around the central giants like mist. It's a reminder that even the galaxies we see as distinct are part of larger structures, their edges not as sharp as we imagine. The formation of such colossal galaxies is an ongoing process. Even today, in the centres of clusters, smaller systems are falling in, adding their stars to the mix. The growth is slow, but it never stops. Over cosmic time, gravity gathers more and more mass into these central giants, while the outer regions of clusters thin out as galaxies are absorbed. In the distant future, each cluster may contain only a single, enormous elliptical, the result of countless mergers. The stars within these giants are mostly old, ancient red and yellow suns that have burned for billions of years. Their supply of gas is long gone, used up in earlier starbursts or expelled by energetic winds. New stars form rarely, if at all. The galaxies glow with a steady, warm light, the cumulative result of countless generations of stellar evolution. To look at one is to see the end point of galactic life, the quiet maturity that follows an age of chaos. Despite their stillness, these galaxies are far from empty. Their cores are bustling with activity at scales we can hardly conceive. Dense clusters of stars crowd the inner regions, and near the black hole, the gravitational pull is so strong that stars orbit at thousands of kilometers per second. The energy released by this central region can heat the surrounding gas to tens of millions of degrees, producing a halo of X-rays that extends for hundreds of thousands of light years. In the Coma cluster, and others like it, these X-ray halos fill the space between galaxies, a sign of the enormous gravitational potential that holds everything together. From our small, spiral perspective, the existence of galaxies like IC1101 or the Coma giants is both awe-inspiring and humbling. They are the extremes of what the universe can build using nothing more than gravity and time. The same physical rules that shape the Milky Way also shape them, only the scale changes. Given enough matter and enough time, Gravity will gather it all into one place, smoothing out the complexity until only the largest, most stable forms remain. These colossal galaxies are the natural culmination of that process. Their role in the universe is significant beyond their sheer size. As the largest gravitational wells in their clusters, they influence the motion of everything around them. They act as anchors, binding the cluster together. They also regulate the flow of gas within the cluster. The hot intracluster medium, composed of ionized gas at millions of degrees, is affected by outflows from the central black holes. These outflows can prevent the gas from cooling and forming new stars, effectively shutting down further star formation on a cluster-wide scale. In this way, the biggest galaxies shape the evolution of their entire environment. Observations of these systems also reveal the presence of enormous quantities of dark matter. The visible stars account for only a small fraction of their total mass. The rest is invisible, detectable only through its gravitational effects. By studying how galaxies move within clusters and how light from distant objects bends as it passes through them, a phenomenon known as gravitational lensing, astronomers can map the distribution of this dark matter. What they find is that the halos of the largest galaxies extend far beyond their visible edges, merging seamlessly into the dark matter halos of their clusters. It's as though the giants are not individual objects but the luminous centres of vast invisible structures. The existence of these colossal systems also helps refine our understanding of cosmic time. Their age tells us something about the universe's timeline of structure formation. The largest galaxies could not have formed in the early universe. There simply hadn't been enough time for mergers to build them. Their presence today, massive and ancient, indicates billions of years of accumulation. Each one is a record of cosmic history, its stars the fossils of earlier eras. By studying their composition and motion, astronomers can trace the story of how matter organized itself from the Big Bang to the present. When you think about them in human terms, these galaxies are almost beyond imagination. Their cores alone can contain hundreds of billions of stars packed into a region only a few thousand light-years across. The light from their outer edges takes millions of years to reach their centers. If you lived on a planet within one of those cores, the night sky would never be dark. Thousands of stars would be visible even in daylight, their light blending into a golden haze. The concept of night and day would blur into a continuous twilight of starlight, and yet, for all their immensity, these galaxies are quiet. They rotate slowly, their random stellar motions cancelling one another out. They've long since used up their fuel for new creation. The brilliance they emit now is the glow of endurance, old stars continuing to shine, long after their most active years have passed. There's a calm to them, a sense of completion. Where the Milky Way still spins and forms new stars, these giants have settled into permanence. They are, in a way, the elders of the cosmos. In photographs taken by space telescopes, they don't always stand out at first. Their light is diffuse, their outlines soft. You only notice their dominance when you realise how far their glow extends, how many smaller galaxies orbit them, how their light fills the centre of the frame. The faint smudges scattered around them are their satellites, each one a survivor of past encounters. The cluster around them is their domain, a city of galaxies held together by their gravity. If we think of the Milky Way as a spiral island, these giant ellipticals are continents. They gather everything nearby, incorporating it into themselves until little remains but their own light. Over time, they'll continue to grow, though at an ever slower pace. The universe is expanding, and the rate of new mergers decreases as galaxies drift farther apart. Eventually, the giants will stand alone, each surrounded by the ghosts of its former companions drifting through the dark. Their existence offers a glimpse of the universe's eventual shape. As cosmic expansion accelerates, distant galaxies will recede beyond visibility. Only bound clusters like these will remain intact, isolated in the vastness. Within each, the central giant will shine as the last great structure, the ultimate product of gravity's work. In that distant future, when most galaxies have merged and most stars have faded, these colossal systems will be the final beacons of light, immense, ancient, and solitary. For now, though, they serve as markers of possibility. They show us how large a galaxy can grow, how far matter can gather under its own pull. They remind us that our Milky Way, for all its size, is part of a continuum that stretches from the smallest dwarfs to these giants. And even though the Milky Way will never reach their scale, its destiny, merging with Andromeda, then absorbing smaller companions, is a small version of the same process. Every galaxy, large or small, follows the same cosmic pattern. When we imagine the great cities of the universe, we might think of places where light gathers in impossible abundance, where entire galaxies crowd together like towers of glass, where space itself seems thick with starlight. These are the cosmic cities, the clusters where hundreds or even thousands of galaxies live bound to one another by gravity. Among them, at the very heart, sit the largest and oldest residents, galaxies so immense that even their outlines blur into the background of the cosmos. At the centre of these crowded regions, one name has become almost symbolic of the extreme: IC-1. IC-1 lives in the Abell 2029 cluster, about 1 billion light-years away from us. Its light left when Earth was still young, when the first multicellular organisms were just beginning to move in ancient seas. What we see today is a snapshot of that distant past, a frozen moment in the life of a structure that has existed for most of cosmic history. Even by the standards of galaxy clusters, IC-1101 is extraordinary. With a diameter of about 6 million light-years, it's roughly 60 times wider than the Milky Way. Its mass exceeds 10 trillion suns, and the number of stars it contains stretches far beyond comprehension, perhaps 100 trillion, though no one can say for certain. Numbers that large are barely numbers anymore. They become metaphors for enormity. To put it simply, IC-1101 is not just a galaxy. It's a small universe in itself. If you placed it where the Milky Way now sits, its edges would reach far beyond the orbit of Andromeda. It would swallow our local group whole, turning every galaxy we know into a single glowing patch inside its vast body. And yet, even IC-1101 is just one among many in the great cosmic metropolises that populate the universe. Each cluster contains its own central giant, each one a gathering point for billions of suns. The story of IC-1101's creation is the story of what happens when gravity is given time and abundance. In the early universe, galaxies were smaller, more chaotic, more prone to collisions. In the densest regions where matter was most concentrated, those collisions happened constantly. Smaller galaxies fell together, merged and grew. Over billions of years, the central region of Abell 2029 became a gravitational well so deep that nothing nearby could escape it. Every time two galaxies met, they lost a little energy to tidal forces and spiraled inward, eventually merging with the one at the centre. Each merger added new stars, new gas, and more mass. The result was IC-1101, a single object built from thousands of ancestors, each one absorbed into the whole. From afar, IC-1101 looks smooth and featureless, like a faint golden ellipse fading into black. Its light doesn't stop suddenly, but tapers off gradually, blending into the diffuse glow of the surrounding cluster. This is one of its defining traits, an extended envelope of stars that stretches far beyond what you might call a boundary. Those outer regions are filled with the debris of past mergers, stars that were stripped from other galaxies and now orbit in long, diffuse paths. There is no clear line between where IC-1101 ends and the intra-cluster light begins. It's as though the galaxy and the cluster are one continuous structure, one luminous body held together by shared gravity. If you could travel within it, the scale would defy every sense of distance we know. The inner regions near the core would be crowded beyond imagination. Stars would be packed thousands of times more densely than in our part of the Milky Way. The sky would never grow dark. Even between the stars, faint glows would fill the air, light scattered by dust and reflected from countless suns. Yet as you moved outward, that density would fade. The outer halo would stretch on for millions of light years, its stars thinly scattered, each one separated by vast spaces of silence. The centre of IC 1101, like most large galaxies, contains a supermassive black hole, but in this case, the word supermassive barely suffices. Estimates suggest it could weigh more than 40 billion suns, possibly more. That's 10,000 times the mass of the black hole at the Milky Way's centre. If placed in our galaxy, it would dominate the entire core, swallowing the orbits of countless stars. Such a black hole likely grew alongside the galaxy itself, fed by the inflow of gas and the merging of smaller black holes from the galaxies it consumed. When it was active, perhaps billions of years ago, it might have shone as a quasar, one of those brilliant beacons visible across the early universe. Now it sits mostly quiet, the remnants of that ancient energy sleeping at the heart of its city of stars. IC 1101 isn't alone in its grandeur. The universe contains other galaxies of comparable size, each sitting at the centre of a rich cluster. These central giants, known as CD galaxies, act like the gravitational capitals of their clusters. They're not just luminous bodies, but anchors, around which hundreds of smaller galaxies orbit. In the Perseus cluster, NGC 1275 fills this role, a galaxy almost 500,000 light-years across, blazing in radio and X-rays due to the activity of its central black hole. In the Coma cluster, NGC 4874 and NGC 4889 share the crown, their combined mass binding thousands of galaxies into one vast gravitational system. In the Virgo cluster, the elliptical M87 reigns, famous for being the first galaxy whose black hole was ever imaged directly, a shadow captured by the Event Horizon telescope, revealing a structure 55 million light-years away, yet as distinct as a ring of fire. Each of these central galaxies is a monument to time. Their stars are old, their gas depleted, their colours golden rather than blue. Most of their visible light comes from long-lived stars that have been shining quietly for billions of years. There are few young, hot stars left. The burst of creation that once filled them has faded. In this sense, the great cosmic cities are places of age and endurance, where the cycle of starbirth and death has slowed to a near halt. They're the universe's elder statesmen, immense, stable, and ancient. Clusters like our Bell 2029, Perseus, Coma, and Virgo are not just collections of galaxies, they're vast ecosystems. Between their galaxies lies hot plasma, a gas heated to tens of millions of degrees by the energy of their motion. This plasma fills the spaces between galaxies, emitting X-rays that we can detect with space telescopes. In that environment, galaxies move like fish through an invisible sea, trailing wakes of hot gas behind them. As they pass through the cluster, the gas in their outer regions can be stripped away, leaving them barren and quenching their ability to form new stars. Over time, many become satellites of the central giant, their individuality slowly erased. The scale of these clusters is almost beyond belief. The Coma cluster, for instance, contains over 1,000 galaxies within a sphere about 20 million light-years wide. The total mass of such a cluster, including its dark matter halo, can exceed a quadrillion suns. The light from one edge to the other takes tens of millions of years to travel. Within those clusters, galaxies move at speeds of up to 1,000 kilometers per second, their trajectories governed by the shared gravity of the whole. And yet, from our perspective, all of this unfolds in perfect silence, slower than thought, quieter than time. The galaxies at the centre of these cosmic cities represent the endpoint of the process that began billions of years ago, with small clumps of matter forming the first stars. They are the result of endless mergers and accretions, the final gathering places for light. Everything about them speaks of accumulation, not sudden creation, but gradual assembly. They've built themselves from everything that has drifted close enough to be captured. Each one is a record of cosmic history written in starlight, a ledger of every smaller galaxy that ever fell into its orbit. The light we see from them today carries that story across unimaginable distances. When astronomers study it, they're looking back in time, seeing the cumulative result of billions of years of cosmic evolution. The smoothness of their glow tells of repeated mergers. The colour of their stars reveals their age. Even their size speaks to the density of the universe's earliest clusters. The more crowded the environment, the faster these giants grew. In the emptier regions where galaxies are sparse, no such giants exist. They are the products of the universe's most fertile regions, the downtown cores of the cosmic landscape. In many ways, they remind us of cities on Earth. Each galaxy within a cluster is like a building, distinct yet part of a whole. The space between them is like the air between towers, vast but still part of the same structure. The central giant is the capital, older and more massive, surrounded by younger, smaller companions that circle like suburbs. Light flows through the cluster as traffic does through streets, crossing distances that to us would seem eternal, but to gravity are nothing more than the hum of its invisible engine. The largest of these cosmic cities continue to shape the universe around them. Their gravity bends light from even more distant galaxies, distorting it into arcs and rings. This effect, called gravitational lensing, allows astronomers to see objects otherwise too faint to detect. Through these lenses, we can peer deeper into the past, glimpsing galaxies that formed when the universe was only a fraction of its current age. In this way, the great cosmic cities act not only as destinations but as windows, their gravity revealing what lies beyond. From the Milky Way, these clusters appear as faint smudges or collections of points through a telescope. The Virgo cluster, our nearest major cluster, lies about 50 million light-years away and contains several thousand galaxies. If you could see it all at once, its central region would be dominated by M87 and its halo of companions. Farther out, spirals like M100 and M99 twist gracefully, their shapes still intact. Beyond Virgo, the Coma cluster marks another dense region. Farther still, and between these great hubs lie filaments of galaxies stretching across space like connective tissue. Together they form the large-scale structure of the universe, the cosmic web, of which the clusters are the nodes, the bright intersections. When we call them cities, it's more than a metaphor. They have hierarchies, histories, and interactions. They grow through trade of gas, stars, and gravity. They expand until they can no longer draw in new members, then they settle, their edges defined by the expansion of the universe. Inside them, smaller galaxies orbit like satellites, and within those galaxies, planets orbit stars. The pattern repeats, from the vastest scales to the smallest, a fractal of motion held together by the same simple force. If you could drift within one of these clusters, you would see light everywhere, faint, distant, overlapping. Galaxies would float in every direction, some round and red, others faintly blue, their shapes distorted by motion and distance. The central giant would glow like a sunrise that never ends, its light diffused through millions of light-years of dust and gas. Space would feel both crowded and endless at once. Every direction would hold depth, every speck of light a collection of worlds, and in that endless, luminous stillness, you might begin to feel something that astronomers sometimes describe but rarely dwell on. A sense of scale that no longer feels measurable, but continuous. The same gravity that holds your feet to the ground on Earth is the same that built IC 11-1. The same laws that govern the motion of planets govern the merging of galaxies. There's no dividing line between the ordinary and the colossal. The universe works the same way everywhere, only on different scales. IC 1101, M87, NGC 4.89. These are the monuments of time. They are the result of billions of years of steady, patient accumulation. They are proof that complexity can arise without chaos, that order can come from gravity alone. They are reminders that the universe is old enough to have built things larger than imagination, but simple enough to be understood by the same physics we use to measure an apple falling from a tree. As we drift away from the centres of these great clusters in thought, leaving behind their dense cores and faint halos, we move into the spaces between them, the cosmic voids. Out there, galaxies are rare, light is scarce, and distances stretch unbroken for hundreds of millions of light years. Yet even those empty regions have their role in the grand design. The clusters and voids together form the architecture of the universe, a balance of presence and absence. There's a point in any exploration of the universe when numbers begin to fail. You can say a galaxy is 100,000 light years wide, or that the Milky Way holds hundreds of billions of stars, and those statements still mean something to the human mind. But as the scale expands beyond clusters and superclusters, beyond the grand cosmic cities and into the architecture of all existence, the measurements stop feeling real. They become sounds we can pronounce but not truly imagine. The mind simply runs out of room, and yet this incomprehensible scale is where the true picture of the universe lives, in the distances so vast that light itself, travelling at the highest speed possible, takes billions of years to cross them. We can start with something tangible, a single light year. It's about 9.5 trillion kilometres, the distance that light covers in one Earth year. That's our basic yardstick for cosmic measurement. Multiply that by 100,000 and you have the width of our galaxy. Multiply again by 2.5 million and you reach Andromeda. Now multiply by 1 billion and you start to approach the scale of the large galaxy clusters, those luminous cities like Abell 2029 or Coma, where hundreds or thousands of galaxies gather. But even that is still small compared to the next step outward. Beyond clusters lie superclusters, vast collections of clusters and groups bound loosely together by gravity. Our own galaxy belongs to a structure called the Laniakea supercluster, a region spanning more than 500 million light years. Inside it, about 100,000 galaxies move along slow, curved paths determined by gravity, all flowing toward a common gravitational centre known as the Great Attractor. The Virgo cluster, which sits about 50 million light-years away, forms part of this structure. The Milky Way and Andromeda, as part of the local group, are on the outer edge of this immense formation, drifting gently inward through a web of cosmic filaments. The size of Laniakea alone is enough to stagger imagination. Its volume is so vast that light would need 500 million years to travel from one end to the other. That means if you could somehow send a beam of light across it at the speed of light itself, it would still be in flight when life on Earth evolved from single-celled organisms into complex animals. The light from one edge would not reach the other until entire ages had passed. And yet, even this supercluster is only a small piece of the universe's larger pattern. When astronomers began mapping the positions of galaxies on a truly large scale, they discovered that they weren't randomly scattered. Instead, they form a web, an intricate network of filaments, clusters, and vast empty voids. The pattern looks almost biological, like the structure of neural tissue or the branching of rivers. Galaxies gather along the filaments, connected by threads of dark matter that span hundreds of millions of light years. Where the filaments intersect, clusters form, dense knots of galaxies like Coma and Perseus. Between these filaments lie enormous regions almost devoid of galaxies, the cosmic voids, some stretching 300 million light-years across. The universe, at its largest scale, is a structure of contrast, dense regions of light woven around dark emptiness. This structure wasn't always there. In the first few 100,000 years after the Big Bang, the universe was nearly uniform, a hot, dense soup of matter and radiation. The differences in density were minuscule. just tiny fluctuations in the cosmic microwave background. But over billions of years, gravity amplified those small differences. Regions slightly denser than average pulled in more matter, growing denser still, while emptier regions lost matter and became voids. The result of that slow amplification is the universe we see today, a vast cosmic web where galaxies are the bright traces of ancient ripples in the early cosmos. On that scale, even galaxies as massive as IC 1101 become details, small points of light in a larger pattern. The distances between superclusters are so great that the entire Milky Way could fit into the space between them many times over. The filaments themselves are unimaginably long, strands of galaxies stretching hundreds of millions of light years, each glowing faintly with the light of billions of suns. Observations from surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey have mapped these structures across billions of light years, showing that the universe resembles a giant foam of light and emptiness. The luminous filaments are the edges of bubbles, and the voids are the hollow spaces between them. When astronomers describe the size of the observable universe, they mean the portion from which light has had time to reach us since the Big Bang. That sphere has a radius of about 46 billion light years. Its diameter, the full span from one side to the other, is roughly 93 billion light years. It's difficult even to phrase that without it sounding absurd. 93 billion light years isn't just a distance. It's an expanse so large that no human language was ever designed to handle it. Every galaxy, every cluster, every supercluster we've ever observed exists inside that sphere. Beyond it, there may be infinitely more, but their light has not had time to arrive. Even within that boundary, the number of galaxies defies intuition. Earlier estimates placed it around 200 billion, but newer data suggest it could be closer to 2 trillion. 2 trillion galaxies, each containing hundreds of billions of stars. Every one of those stars, on average, hosts at least one planet. That means the observable universe could contain more worlds than there are grains of sand on every beach on Earth. And yet, all of that fits within the cosmic horizon defined by the finite speed of light. Everything beyond remains invisible, expanding away faster than light can bridge the gap. This scale doesn't only challenge imagination, it challenges comprehension itself. The mind can picture a planet, it can picture a solar system, maybe even a galaxy, but it can't truly hold the scale of the universe. Even scientists who study cosmology often admit that the numbers are less about understanding and more about measurement. We can write them down, but we can't feel them. The scale of the incomprehensible is not something the mind inhabits. It's something it glances at and steps back from, the way one might look over the edge of a great height. To make it more approachable, astronomers often use analogies. If the Milky Way were reduced to the size of a dinner plate, the Andromeda Galaxy would be another plate 2 feet away. The entire local group would fit inside a small room. The Virgo cluster would fill a large city. The Laniakea supercluster would span continents. And the observable universe, everything we can see, would be the size of Earth itself. Within that metaphor, the Milky Way becomes one of the tiniest details on a map too large to ever unfold completely. But even that analogy falls short because it still assumes physical scale that can be held in mind. The true challenge of the universe's immensity is not that it's large, but that it's continuous. Every part of it connects to every other part through time, through gravity, through the shared expansion of space. The same physics that shapes an atom's orbit shapes a galaxy's spin. The same principles that govern the sun's light govern the evolution of the entire cosmos. On the scale of the incomprehensible, everything that exists shares one origin and one fate. Cosmologists use mathematical models to describe this vastness. The universe's expansion, first observed by Edwin Hubble, means that distant galaxies move away from us faster the farther they are. The relationship between distance and velocity defines the Hubble constant, a value that measures the rate of expansion. When we observe galaxies at extreme distances, we see their light stretched by that expansion, redshifted into longer wavelengths. The most distant galaxies we've detected have redshifts so high that their light has been stretched more than tenfold, meaning the universe has expanded more than 10 times since their light was emitted. That's how we know how far and how long we're looking into the past. At these scales, even light, the fastest thing in existence, becomes a slow traveller. The light from the most distant galaxies in the Hubble Deep Field left when the universe was less than 1 billion years old. Since then, it has crossed expanding space, its wavelength stretched, its energy thinned, yet still it arrives. When we see those faint smudges, we're seeing history itself, not as memory, but as living light. The incomprehensible becomes slightly more real when we realise that it's not abstract at all. It's visible right now in the faint glow of distant galaxies whose light still reaches our eyes. And yet there's a deeper layer of incomprehensibility. The universe doesn't just have size, it has time. The age of the universe is about 13.8 billion years, but because of expansion we can see galaxies whose light has travelled for that long, and yet are now much farther away than 13.8 billion light years. The space between has stretched as the light moved, turning time into distance. In cosmology, space and time are not separate. They are part of the same continuum. The farther we look, the older the light, and the older the light, the farther the source has receded. The universe is not static and scale is not constant. It grows while we observe it. Even the smallest numbers within this immensity are extraordinary. Take a single cubic meter of intergalactic space, apparently empty. Inside it, there are on average only a few atoms, but there's also dark matter and dark energy, invisible components that make up the vast majority of the universe's mass and energy. Ordinary matter, the stuff that forms stars, planets, and people, makes up less than 5% of everything. The rest is unseen. Dark matter provides the scaffolding for galaxies and clusters. Dark energy drives the expansion of space itself. When we talk about scale, we're not just describing distance, but the structure of everything that fills that distance, both visible and invisible. The incomprehensible scale of the universe also has a strange consequence for our sense of significance. On one hand, it makes us seem impossibly small. A species living on a thin crust of rock orbiting an average star in an ordinary galaxy. On the other hand, it places us within something vast, continuous, and lawful. The same rules that govern the greatest galaxies govern us too. We are not separate from the immensity. We are part of it. Our smallness doesn't remove us from the universe's story. It locates us within it. Even our attempts to measure the universe reveal how connected we are to it. The atoms in our bodies were forged in stars. The energy that powers our cells is the same energy that fills space as radiation. The carbon we breathe out is older than the sun. The calcium in our bones was born in the core of a supernova. We are made of the same matter that fills the galaxies, arranged in a temporary pattern of awareness. The incomprehensible scale doesn't exclude us. It includes us completely. Astronomers sometimes say that the universe is not infinite but unbounded, meaning that it may have no edge, but it also may curve back on itself like the surface of a sphere. On the scale of the incomprehensible, the idea of direction loses meaning. There is no centre, no edge, no up or down. Every point is as valid as any other. From every galaxy, the universe looks the same on the larger scales. It's a principle called cosmological isotropy, and it means that no matter where you are, you're at the centre of your observable universe. From Andromeda, the cosmos would look just as it does from the Milky Way. From IC 1101 the same. Each observer stands in the middle of a vast sphere of light defined only by time and distance. When you consider that, the incomprehensible starts to feel less distant and more intimate. Every point in space is equally a centre, and every moment of time is part of the same unfolding. The incomprehensible scale of the universe is not just about size, it's about unity. It's about the fact that everything, from the smallest particle to the largest cluster, participates in the same cosmic event. The distances are unfathomable, but the connection is immediate. If you could somehow step outside the universe and look back, you wouldn't see a structure with borders or corners. You'd see something smooth and continuous, glowing faintly with the light of uncountable galaxies, stretching endlessly in every direction. It wouldn't be possible to measure it, only to recognize that it exists. And perhaps that's what makes it incomprehensible. Not that it's too big to imagine, but that it's too complete to separate into parts. It's all of it at once. When we return our thoughts from that scale to the smaller one, back to galaxies, to stars, to our own planet, nothing has changed except perspective. The universe is still the same. The numbers we use are only tools for describing what can't be contained by numbers. The incomprehensible isn't meant to be conquered by understanding. It's meant to be experienced as the natural condition of existence. And somewhere in that vast continuum, in one quiet spiral among trillions, a small species is awake in the dark, measuring, imagining, and whispering stories to itself about what it sees. That act alone, of noticing, of thinking, of wondering, connects the smallest mind to the larger scale. The incomprehensible becomes something you can feel, not as size, but as belonging. If you were to stand somewhere in deep space far from any single galaxy and look around, you might think the universe is mostly empty. In most directions, there would be nothing visible at all. The light of distant galaxies would be faint, the blackness unbroken. But invisibly, silently, everywhere around you, gravity would still be at work. It is the most patient and universal of all forces, and the one that gives structure to everything, from the smallest cluster of stars to the grandest web of galaxies. Without gravity, the cosmos would have no pattern. There would be no galaxies, no stars, no planets, and no life to wonder about them. When we speak about the gravity of crowds in the cosmic sense, we're talking about how mass behaves in company. A single star exerts a pull on space around it, curving the fabric of space-time slightly. A galaxy, with hundreds of billions of stars, curves it more profoundly. A cluster of galaxies bends space like a great depression in a vast sheet. The more mass that gathers, the deeper the curve becomes and the stronger its influence grows. The universe is, in essence, a collection of such curves, overlapping, blending, and shaping one another. A landscape of invisible valleys and ridges defined entirely by gravity. Galaxies are social creatures by nature. They rarely exist alone. They cluster together because their combined gravity draws them in. The smallest groups contain a few dozen members, the largest, thousands. Within those crowds, galaxies move as if caught in a slow dance, their paths bending around the shared centre of mass. The result is a dynamic equilibrium, motion balanced by attraction. Each galaxy is an actor in a play directed entirely by gravity's script. On human scales, gravity feels weak. It's what holds us to the ground, what keeps planets in orbit, but it's easy to forget that it's the same force that holds the entire universe together. The reason it feels weak here is because it's always divided among so many things. But in the collective, when mass accumulates in great numbers, its effects multiply. The crowd amplifies its own pull. This is the gravity of crowds, the way that many small influences combine into something vast and enduring. In galaxy clusters, this collective gravity shapes everything. The galaxies themselves are just the visible part. Most of a cluster's mass lies in two unseen components, hot gas and dark matter. The gas, heated to tens of millions of degrees, glows in X-rays, filling the space between galaxies. The dark matter, though invisible, forms an even larger halo that binds the cluster together. Without it, the galaxies would move too fast to remain bound. The fact that they don't fly apart is one of the earliest clues scientists had that dark matter exists. The distribution of mass in these clusters is not uniform. The galaxies form the luminous skeleton, but the true structure is defined by the dark matter halo, which extends far beyond what we can see. It's this halo that determines how the galaxies move, how fast they orbit the centre, and how they interact. It also affects the way light travels through the cluster. When light from more distant galaxies passes by, it bends, creating distorted images or arcs, a phenomenon known as gravitational lensing. Through this effect, astronomers can map the otherwise invisible dark matter. The shapes of those arcs reveal the contours of gravity's landscape, showing how mass bends space like glass bends light. The crowd's gravity doesn't just hold galaxies together, it changes them. When galaxies move through a cluster, they interact not only with one another, but also with the hot plasma that fills the space between. The gas acts like a wind, stripping material from galaxies as they move through it, a process known as Ram pressure stripping. The result is that spiral galaxies entering clusters often lose their outer gas, halting new star formation and transforming them over time into lenticular or elliptical shapes. The crowd reshapes its members simply by existing. In the densest clusters, collisions are common. As galaxies pass close to one another, their gravity distorts their shapes, pulling out long streams of stars and dust. Some merge completely, forming larger systems. Others are torn apart, their stars scattered into the intra-cluster space. Over billions of years, these interactions build up the central giant galaxies that dominate cluster cores. The crowd feeds its leaders, transferring mass inward. It's a slow, relentless process, one that transforms the cluster's structure and colour. The longer a cluster exists, the redder it becomes, as star formation slows and older stars take over. The most massive clusters in the universe, those with names like Coma, Perseus, and Abel 1689, are defined by this collective gravity. They are the crowded hearts of the cosmic web, the nodes where filaments of galaxies converge. Each cluster contains not just galaxies, but enormous reservoirs of hot gas, and together, those components outweigh all the visible stars combined. Yet even with that, the majority of their mass is still dark matter, invisible but measurable through its pull. Gravity has a peculiar property that sets it apart from the other forces of nature. It never repels, it only attracts. The more matter you have, the more it pulls, and the more it pulls, the more matter gathers. It's a feedback loop written into the fabric of space itself. This is why the universe looks the way it does, not evenly spread but clumped into structures. Wherever matter gathered slightly more than average in the early universe, gravity made that imbalance grow. Over time, those slight excesses became galaxies, clusters, and the large-scale filaments that now form the cosmic web. In the modern universe, the gravity of crowds continues to shape the motion of everything. Galaxies in a cluster orbit the common centre, much as planets orbit stars, though at vastly different speeds and scales. A typical galaxy in a cluster may move at more than 1,000 kilometers per second, taking billions of years to complete one orbit. These motions are so slow that from our perspective the cluster seems frozen in time. But on scales of hundreds of millions of years, everything within it is in motion, every galaxy tracing its long, slow path through the gravitational field of all the others. Clusters themselves are not isolated either. They gather into larger structures, superclusters, which are even more loosely bound. The Laniakea supercluster, which includes our own local group and the Virgo cluster, is one such structure. Within it, thousands of galaxies and dozens of clusters move along filaments of dark matter, flowing toward a region of higher density called the Great Attractor. This motion is not random. It's part of the universe's overall architecture. Gravity organizes movement on every level, from the orbit of a moon to the drift of superclusters. To picture the gravity of crowds is to imagine a vast invisible ocean in which everything floats. Each concentration of mass creates a small current, a subtle flow in space-time. Where many such currents meet, they merge into larger ones. Over billions of years, these flows sculpt the universe's shape. The galaxies we see are like the foam on the surface of that ocean, tracing the motion of something far deeper and more powerful. On smaller scales, gravity behaves the same way. Within the Milky Way, the combined gravity of all its stars holds the disk together, balancing the outward motion of rotation. Within a single star cluster, the mutual attraction of a few thousand suns keeps them orbiting their shared centre. The pattern repeats downward endlessly. Whether it's a handful of stars or 100 trillion, the rules are the same. What changes is only the scale, not the law. Even within galaxies, the crowd's gravity influences behaviour. In the Milky Way's disk, the collective pull of billions of stars creates waves that move through the spiral arms. These density waves compress gas clouds and trigger new star formation, maintaining the spiral pattern over time. It's another form of the same principle, individual stars acting together to create something larger than any one of them. At the largest scales, the gravity of crowds extends beyond what we can see. The cosmic web itself, the filaments of galaxies and dark matter stretching across the universe, exists because of this collective pull. The galaxies along those filaments move slowly toward the nodes where clusters reside, feeding them like rivers feeding a lake. This process, called hierarchical formation, continues even now. Smaller structures fall into larger ones merge into greater wholes. The universe is still assembling itself, guided by the same gentle insistence that has shaped it from the beginning. One of the most striking ways we can observe the gravity of crowds in action is through gravitational lensing on the scale of clusters. When light from a background galaxy passes near a massive cluster, the curvature of space-time bends its path. To us, the distant galaxy appears stretched, magnified, or multiplied into arcs and rings. These distorted images, sometimes forming complete circles called Einstein rings, are direct evidence of how mass warps space. In some clusters, the effect is so strong that it acts as a natural telescope, letting astronomers see galaxies far beyond what even the most powerful instruments could normally detect. The crowd's gravity not only binds its members together, it reveals more of the universe beyond. This same phenomenon happens on smaller scales too. Even individual galaxies can act as lenses, magnifying the light of more distant systems. But in clusters, where the mass is immense, the lensing effect becomes a cosmic work of art. The arcs and spirals of distorted light trace the outlines of invisible dark matter, allowing scientists to map its presence with extraordinary precision. It's one of the few ways we can observe something that otherwise cannot be seen. The behaviour of clusters also tells us about the universe's fate. The collective gravity of all matter, both visible and dark, works against the expansion of space. For much of cosmic history, the pull of gravity slowed that expansion. But about 5 billion years ago, something changed. Observations show that the expansion began to accelerate, driven by what we call dark energy, a mysterious form of energy that permeates all of space and pushes it outward. Gravity tries to pull things together, but dark energy drives them apart. The universe's structure today is a balance between these two opposing forces, the crowd's inward pull and the cosmic outward push. In the far future, this tension will define the shape of everything that remains. As the expansion continues, clusters like Virgo and Coma will become isolated islands, their gravity no longer able to reach beyond their immediate boundaries. Distant galaxies will slip away faster than light, disappearing beyond the cosmic horizon. The gravity of crowds will still bind the galaxies within each cluster, but the clusters themselves will drift alone in the dark, their local harmony preserved even as the universe grows more empty. If you step back and think of it all at once, the galaxies, the clusters, the filaments, the web, it's clear that gravity is not just a force, but a sculptor. It doesn't act suddenly, it doesn't command, it simply persists. Over billions of years, it turns the chaos of the early universe into order. It arranges, it collects, it steadies. The gravity of crowds is the quiet rhythm that underlies everything that exists, and within that grand crowd of matter, we are part of it. Every atom in our bodies contributes, however faintly, to the curvature of space-time. The Earth's gravity binds us to it. The Sun's gravity binds the planets. The galaxy's gravity binds the stars, and the cosmic web binds the galaxies themselves. It's an unbroken chain of connection that stretches from the smallest scale to the largest. The same rule that governs the orbit of a falling apple also governs the motion of superclusters. So when you think of the universe's enormity, the incomprehensible distances, the endless expansion, the silent drift of galaxies, it helps to remember that all of it is held together by something simple. Gravity doesn't need to shout to make itself known. It only needs time. Given enough time, it gathers everything into patterns, and even when those patterns fade, the influence remains. The gravity of crowds is not just a description of the universe's structure. It's the story of how everything finds its place, how all things, no matter how far apart, remain connected through the same invisible thread. And though we can't see that thread, we can feel its presence. In the orbit of our world, in the falling of tides, in the gentle stability of the stars above, the crowd extends outward infinitely, and we are one small part of its collective pull. Every time we look at the night sky, we are not seeing things as they are, but as they were. Every star, every galaxy, every glimmer of light has taken time to reach us, and the farther away it is, the longer that journey has been. When we see the moon, we're seeing it as it was about 1¼ seconds ago. When we look at the sun, we're seeing it as it was 8 minutes ago. The light from the nearest star, Proxima Centauri, has been travelling for more than 4 years, and when we look at the faintest galaxies at the edge of the visible universe, we are seeing light that began its journey more than 13 billion years in the past, long before the Earth existed. Light, distance, and time are not separate things in the universe. They are different ways of describing the same reality. Every measurement of distance in astronomy is really a measurement of time, how long it takes light to cross that distance. And because light moves at a fixed speed, about 300,000 kilometers every second, it becomes the cosmic clock by which we measure everything. When astronomers speak of light years, they are speaking not only of space, but of history. That connection means that when we observe distant objects, we are looking back into the past. The farther away something is, the older the light we see from it. This is why telescopes are not just tools for seeing farther, but for seeing earlier. They allow us to look into the deep time of the universe, to witness galaxies forming, stars igniting, and the first structures coming together out of the cosmic dark. It's not just distance we observe, but the unfolding of time itself. Even nearby, light reveals the universe's patience. The sunlight that warms our planet comes from photons created in the core of the sun, where hydrogen fuses into helium under immense pressure and heat. But those photons don't travel straight from the core to the surface. They scatter countless times inside the dense plasma, absorbed and re-emitted over and over. It can take hundreds of thousands of years for a single photon to make that journey from the sun's core to its surface, and then just 8 minutes more to cross the empty space to Earth. The sunlight that touches your face today may have been born when early humans were first learning to use fire. On larger scales, this same delay between event and observation becomes the fabric of astronomy itself. When we observe the Andromeda Galaxy, we are seeing it as it was 2.5 million years ago. When that light left, the first ancestors of modern humans were walking the plains of Africa. The galaxies we see in the Hubble Deep Field, those faint smudges billions of light years away, are glimpses of the universe when it was young, less than 1 billion years after the Big Bang. The farther we look, the younger the cosmos appears. The universe, in that sense, is like a memory frozen in light. This is one of the profound consequences of the finite speed of light. Space and time are woven together. The farther you look in distance, the further back you look in time. The night sky is not a single moment. It's a tapestry of moments spread across billions of years. Some of the stars we see have already died, their light still on its way. Some of the galaxies we observe no longer exist in the form we see them. We live surrounded by the ghosts of the past, their messages still arriving long after the events have ended. The relationship between light, distance, and time also defines the shape of the universe itself. According to Einstein's theory of relativity, space and time are not separate but part of a single continuum called space-time. Massive objects like stars, galaxies, and clusters warp this fabric, and light follows those curves. When we measure light's travel through the universe, we are tracing its path through that warped geometry. The apparent distance between 2 points depends on how space-time itself has stretched and curved along the way. Because the universe is expanding, light travelling across it is stretched as well. This stretching shifts the light toward longer wavelengths, a phenomenon known as redshift. The greater the distance, the greater the redshift, and the older the light. This is how astronomers determine how far away a galaxy is and how fast the universe is expanding. A galaxy's light carries a record of how space itself has stretched during its journey. When light left a galaxy billions of years ago, it was a certain colour, corresponding to a specific wavelength. As it travelled, the expansion of the universe stretched that wavelength, making it redder. By measuring that shift, astronomers can calculate how long the light has been travelling, and how much the universe has expanded in that time. Every beam of light, every photon that reaches us carries this information, the imprint of cosmic motion written directly into its colour. The most ancient light of all comes from the cosmic microwave background, the faint afterglow of the Big Bang itself. It fills the universe in every direction, a soft radiation left over from the time when the universe first became transparent, about 380,000 years after its beginning. Before that, matter and radiation were so tightly coupled that light could not travel freely. When the universe cooled enough for atoms to form, light was finally released, and it has been travelling ever since. That ancient light now reaches us as microwaves, its wavelength stretched by more than 1,000 times by the expansion of space. It is the oldest light we can ever see, a snapshot of the universe when it was still glowing with its first heat. From that point onward, light has been our messenger. Every observation we make, whether it's a star, a planet, or a distant galaxy, comes to us through light. Even the information gathered from other forms of radiation, like X-rays or radio waves, is still a part of the same electromagnetic spectrum. We have never seen the universe directly. We have only ever seen its light. Every detail we know about distant stars, every image of a faraway galaxy, is light that has crossed unimaginable distances to tell us what once was. It's easy to forget that light doesn't simply exist in space, it travels through it. And as it travels, it experiences the universe's history. Light is influenced by gravity, by expansion, by motion. It bends around massive objects, slows slightly as it passes through gravitational wells, and redshifts as the space between galaxies stretches. When we observe the cosmos, we're looking not through a static window, but through a moving, expanding medium that distorts and carries every image across billions of years. If we could see light's journey as a line through space-time, it would look like a thread weaving through an ever-stretching fabric. It would start at some distant source, a supernova, a star, a quasar, and travel forward while the space it passes through expands beneath it. The light itself always moves at the same speed, but the universe's growth stretches its path, increasing the distance it must cross. Some photons never make it. The expansion of space carries their source away faster than they can reach us. Those photons will travel forever without ever arriving, their messages lost to the cosmic horizon. The cosmic horizon is the limit of what we can see, the boundary beyond which light has not had enough time to reach us since the beginning of the universe. It's not a physical wall, but a temporal one. Every second, light from slightly farther regions becomes visible, but at the same time, expansion carries more distant regions beyond reach. The observable universe is constantly changing, expanding, and yet limited by this interplay between light's speed and the universe's growth. What lies beyond it is forever invisible to us, though we know it must exist. This relationship between light, distance, and time also means that the universe looks different depending on how far away we look. Nearby galaxies show us the universe as it is today, mature, structured, filled with large clusters and old stars. Farther away we see younger galaxies, smaller and bluer, forming their first generations of stars. The deepest observations show galaxies in the act of assembling, still clumpy and irregular, their light reaching us from a time when the universe was only a few 100 million years old. Looking outward is looking backward. The telescope is a time machine, and light is its mechanism. Even within our own galaxy, light reveals distance through time. When we observe supernova remnants like the Crab Nebula, we're seeing the aftermath of a star that exploded nearly 1,000 years ago. Chinese astronomers recorded the event in 1054, and the light from that explosion still spreads outward, illuminating the surrounding gas. When we look at that nebula now, we're seeing the continuing story of that same event, light still arriving, long after the initial flash. On larger scales, we see supernovae in distant galaxies that exploded billions of years ago, their light only now reaching us. Each one is a signal from the past, a record of a moment that once was. The finite speed of light has another curious effect. Simultaneity becomes relative. Two events that seem simultaneous from one perspective may not be from another, because the light from each takes different amounts of time to reach an observer. On cosmic scales, now becomes a local concept. There is no universal present moment shared across the universe. Every point in space has its own timeline, its own version of the unfolding. The light that reaches us from the edge of the observable universe left long before the Milky Way even existed. To see it is to see a time before our own origin. This lack of simultaneity gives the universe a layered texture. Every patch of light we observe corresponds to a different era, a different stage of evolution. The cosmic web we map today is really a composite of billions of years of history seen all at once. The galaxies that appear next to each other in the sky may in reality be separated by hundreds of millions of years in time. The sky is not a flat image, but a temporal landscape, one where every point represents a different age of the universe. In this sense, astronomy is not just the study of space, but of time's geography. Light gives us a way to chart the past, to reconstruct the sequence of events that led from the early universe to now. By observing galaxies at different distances, scientists can build a kind of cosmic timeline, tracing how matter assembled, how stars formed, how elements were created. The entire history of everything we know is written in the light that fills the sky. Even the darkness between stars is not truly empty of light. It's filled with faint radiation, the relic photons of the early universe, the glow of distant galaxies too faint to see individually, the whisper of energy from ancient stars long extinguished. Every cubic meter of space contains hundreds of these ancient photons, moving endlessly, carrying with them the history of everything that has ever emitted light. And on smaller scales, the same principle continues. Light from distant stars takes years, centuries, or millennia to reach us, depending on their distance. When we look up, we're seeing a layered record of time. Some of those stars may already be gone, their light still on its way. Others are newly born, their glow just beginning to spread. The night sky is not the universe as it is, but as it was. A living archive of the past projected onto the present. In that realization there's a strange comfort. We exist within a universe that remembers itself. Every photon that has ever left a star continues on, carrying its story forward through time. Every beam of light is a record, and every observation is a form of reading. Even when the source is gone, the light remains. The distances may be incomprehensible, the timescales unimaginable, but the connection is immediate. We are seeing what once was, and through it, we understand what is. And because light travels only forward, Everything we see is history arriving. The stars above us, the galaxies in the deep field, even the faint afterglow of the Big Bang. All of them are pieces of a single, continuous journey. Light doesn't hurry, it doesn't slow, it just moves, carrying with it the record of time. The universe, vast and ancient, writes its story not in words or sounds, but in light, and we, on our small planet orbiting one star among billions, are here to read it. For all the enormity of what lies beyond, it is easy to forget how small a corner of the universe we actually occupy. Every map of galaxies, every chart of clusters and superclusters, places us somewhere inside it all, a single point along one of the filaments of the cosmic web. That point is our galaxy, the Milky Way, and within it, halfway out along one of its spiral arms, lies a faint yellow star, our Sun. Around it, a handful of planets circle, one of which has the precise balance of temperature, distance, and chemistry to support the fragile phenomenon we call life. From a cosmic perspective, our position is ordinary. There is nothing at all exceptional about our star. It is not one of the largest or the smallest. It sits quietly on the main sequence, a mid-sized star among hundreds of billions. Our planet orbits it in a zone that just happens to allow liquid water, not too close to boil it away, not too far to freeze it solid. The atmosphere that wraps around us is thin, fragile, easily disturbed, and yet it's what allows us to exist at all. Within it, molecules arrange themselves into patterns that think, remember, and ask questions about their own origin. In that sense, our place is not defined by where we are in space, but by the delicate balance that allows us to notice it. When we look out at the night sky, we're not just seeing distance and time. We're seeing from a very particular vantage point, one that's both privileged and precarious. The Earth sits within a stable orbit, protected by Jupiter's gravity from many of the asteroids that might otherwise strike it. The tilt of its axis gives it seasons, distributing warmth in ways that nurture diversity. The Moon stabilizes that tilt, keeping our climate relatively steady over long stretches of time. The magnetic field generated by our planet's molten core shields us from the charged particles streaming from the Sun. Each of these conditions could have been otherwise. Together they create a narrow corridor of habitability. Step too far in any direction, too close to the Sun, too small a planet, too thin an atmosphere, and the balance fails. The fragility of that balance becomes clearer when we look beyond our solar system. The galaxy is filled with stars, many of them orbited by planets. Astronomers now know that nearly every star has at least one. There are rocky worlds, gas giants, icy spheres, and strange combinations of all three. Some orbit so close to their stars that their surfaces glow red hot, while others lie so far away that their atmospheres are frozen in place. A few, scattered here and there, may resemble Earth in size and temperature, but none, as far as we know, carry the same intricate layering of life, air, and water that makes our world so distinctive. Part of what makes Earth's position special is its relative calm. Our solar system lies in one of the Milky Way's spiral arms, but not near its crowded centre. The galactic core is dense with stars, supernovae, and radiation, a dangerous neighbourhood for fragile organisms. Out here, 25,000 light-years from the centre, space is quieter. The density of stars is lower, the rate of cosmic events less intense. It's a place where long, uninterrupted stretches of stability are possible. Life has had billions of years to evolve here, largely undisturbed. Yet this stability is not permanent. The galaxy itself moves. Our solar system orbits the Milky Way centre once every 230 million years, travelling through different regions of its spiral structure. Sometimes we pass through dense regions filled with interstellar clouds. Other times, we drift through emptier space. Over those immense timescales, conditions change. Star formation waxes and wanes. Cosmic rays rise and fall. Even the slow oscillation of our solar system above and below the galactic plane may influence the climate on Earth, subtly shifting the environment in cycles far longer than any human civilization. To the galaxy, these motions are unremarkable, but to us, they are everything. They define the setting in which life emerged. The delicate equilibrium that makes our world habitable depends not just on local conditions, but on the galaxy's broader environment, the radiation levels, the stability of nearby stars, the absence of catastrophic events. If a supernova exploded too close, or if a giant molecular cloud passed through our system, the balance could be disrupted. That it hasn't for billions of years is a quiet kind of fortune. Even within our solar system, the conditions that allow life are narrow. Venus, just one planet closer to the Sun, is a lesson in what happens when that balance tips. With a dense carbon dioxide atmosphere and surface temperatures hot enough to melt lead, it's a world of runaway greenhouse effect. Mars, one planet farther out, is a frozen desert, its thin atmosphere unable to retain heat or pressure. Between them lies Earth, the narrow middle, the just right distance, the small interval where chemistry found a way to become biology. From a distance, that narrowness would be invisible. To someone looking from another star system, Earth would appear as a faint blue dot orbiting an unremarkable yellow star. That dot contains oceans, continents, weather systems, and billions of living things, yet all of it would blend into a single pixel of light. That fragility, the fact that everything we are can be reduced from afar to a single flicker, is part of what makes our place so remarkable. When spacecraft like Voyager 1 turned their cameras back toward Earth after leaving the solar system, they captured that image, a pale blue dot suspended in darkness. From that perspective, there are no borders, no distinctions, no signs of division, just one planet, small and solitary, illuminated by a distant sun. The entire history of humanity, every life, every civilization, every thought, exists within that faint shimmer. For all our size and complexity, we are still contained within a fraction of the cosmos. This doesn't make our place insignificant, it makes it improbable. Against the backdrop of galaxies that stretch for millions of light years and clusters that contain thousands of them, our world is an exception. A place where the universe has become aware of itself. Out of matter and light, out of the same forces that govern the movement of galaxies, has come the capacity to see, to think, to understand. The Milky Way does not know it exists, but one of its planets does. The beauty of our place lies in that connection between the immense and the intimate. The same physics that moves galaxies also stirs the wind. The same gravity that binds clusters holds the oceans to their basins. The same atoms that make up the stars make up our bodies. The difference is scale, not substance. The carbon in our cells was born in the cores of ancient stars, scattered through space by supernova, gathered again into clouds that form the sun and planets. Every breath we take contains atoms older than our solar system. We are, in a literal sense, made of the universe itself. This continuity between ourselves and the cosmos is part of the fragile beauty of our position. The universe is vast beyond understanding, but it is not indifferent. The laws that govern its largest structures are the same that allow for chemistry, for life, for thought. That unity is what makes it possible for us to comprehend it at all. If the universe were governed by chaos, we could not exist to observe it. The fact that it is lawful, consistent and stable enough for consciousness to arise within it is extraordinary. Our planet's fragility becomes clearer the more we learn about others. The study of exoplanets, worlds orbiting distant stars, has shown how rare it may be to find the same combination of conditions we enjoy here. Some planets are locked with one face always toward their star, one side scorched and the other frozen. Some are gas giants without solid surfaces. Some orbit unstable stars whose radiation would strip any atmosphere away. A few lie within what astronomers call the habitable zone, where liquid water could exist, but habitability depends on much more than distance. the thickness of the atmosphere, the presence of magnetic protection, the composition of the planet's crust, all of these must align just right. Even on Earth, that balance is not permanent. Climate, tectonics, and biology interact in complex feedback loops that can shift the planet's equilibrium. Ice ages come and go, continents drift, species rise and fall. Over billions of years, the sun itself will change, growing brighter as it ages. In about 1 billion years, the increased heat will likely evaporate the oceans. In 5 billion years, the sun will expand into a red giant, engulfing the inner planets. Our place, so seemingly stable, exists within a temporary window of cosmic time. That impermanence doesn't diminish its value. If anything, it heightens it. To exist in a universe where conditions change over billions of years, and to find ourselves in one of the few moments and locations where life can flourish, is remarkable. We are part of a rare interval, a chapter in the universe's long story when stars still shine, when planets still orbit, when life still has time. The window will eventually close, but we are here now, able to witness it. The beauty of our place is also in its perspective. From the surface of Earth, we see the universe as a dome of stars overhead, but from space, that dome becomes a sphere, the Earth surrounded by blackness. Astronauts who have seen it from orbit often describe a feeling known as the overview effect, a sudden awareness of the planet's unity and vulnerability. From that distance, national borders disappear, clouds drift freely, and the thin line of the atmosphere glows like a fragile shell. All of human history, all of life, contained within that delicate boundary. It's easy, under ordinary light, to forget how thin that layer is, only about 100 kilometers thick, thinner in proportion to the Earth's size than the skin on an apple. Within it, all weather, all breath, all sound, all movement of life occurs. Above it, there is only silence and radiation. The same gravity that holds the galaxies together also holds this thin air in place. If it were much weaker, the atmosphere would drift away. If it were much stronger, the planet might have never cooled enough for life. Every detail aligns in a narrow corridor of possibility. Even the moon, orbiting at just the right distance to create tides without destabilizing the Earth's rotation, contributes to that balance. The tides stir the oceans, distribute nutrients, and may have played a role in the origin of life along ancient shorelines. The relationship between the Earth, the moon, and the sun is one of harmony, gravitational, thermal, and visual. Together they create the rhythms that define our days and years, the cycles by which all living things measure their existence. In the vastness of the universe, this small system, one star, a handful of planets, one with life, seems almost impossibly specific, and yet it exists. The same processes that built IC 1101 and the great cosmic cities also built this tiny blue world. The same gravitational laws that bind galaxies gave rise to the orbit that sustains us. The same light that travels for billions of years across intergalactic space warms the leaves of trees. The universe doesn't build things separately. It builds them all together using the same tools everywhere. So when we speak of the fragile beauty of our place, we're really describing the intersection of scales, the meeting point of the infinite and the intimate. We live in a galaxy among billions, yet our lives unfold within a few dozen kilometers of breathable air. We belong to a universe that has existed for nearly 14 billion years, yet our entire species has existed for a fraction of that time. Our place is fragile because it is temporary, delicate because it depends on balance, beautiful because it exists at all. And despite the enormity of everything beyond, this small planet remains, for now, the only place we know where the universe looks back at itself. The light that has travelled billions of years to reach us ends its journey in our eyes, in the same fragile creatures who build telescopes, who measure, who wonder, and who rest beneath the stars. That is the quiet miracle of our position. Not that we are central or large or powerful, but that we are here, aware and capable of seeing. If you could stand outside the Milky Way and look back toward it, you would see a broad, graceful disk of starlight turning slowly in the dark. It would seem calm from that distance, a quiet whirl of light about 100,000 light-years across, its spiral arms glowing faintly with the mixed light of hundreds of billions of stars. From where we are inside it, that structure is invisible. We see it from within as a band of milky brightness that stretches across the night sky, a soft blur of stars too numerous to count. It's easy to forget that what we see as a thin streak of light is the side view of an entire galaxy, our home in the universe. Every point of light in that band is another sun, and most of those suns have planets. Some of them are small and rocky, some are gas giants, some might be places where life has found a foothold, quietly evolving under unfamiliar skies. Our own star is just one among them, halfway out along one of the spiral arms, orbiting the galactic center at about 220 kilometers per second. It takes the Sun about 230 million years to make one full rotation around the galaxy, a journey so long that it has completed only about 20 trips since it formed. Every living thing on Earth, every species that has ever existed, has shared this slow voyage together, drifting through space as passengers on a small planet, circling an average star inside a much larger whole. Our position in the Milky Way is not unique, but it is particular. We are far enough from the crowded core that the night sky is stable and calm, yet close enough to the spiral arms that we can see the density of stars that make up the galactic disk. Our solar system sits inside a region of relatively low dust, which gives us a clear view outward. If we were deeper inside the galaxy's center, we would see a sky so filled with starlight that night would barely exist. Here, the stars are separated enough that darkness still has meaning. From this vantage point, light and distance combine to create everything we know as night. The stars we see are spread across thousands of light years, their light arriving at different times. Some are young and hot, others old and fading. The faint band of the Milky Way above us is the combined glow of hundreds of billions of these suns, their light merging together into a soft, continuous haze. Every night, when you look up, you are seeing a cross-section of the galaxy, a view through its spiral disk. The light that reaches your eyes began its journey thousands, tens of thousands, even hundreds of thousands of years ago. You are seeing the galaxy's past arriving now. It's remarkable to think that our species, which has existed for only a few 100,000 years, has spent almost all that time looking up. Before we knew what galaxies were, before we could measure light or distance, we still felt their presence. The stars were the first map, the first mystery, the first measure of time. Civilizations rose and fell beneath that same strip of light, unaware that they were inside it. Only recently, in the scale of cosmic history, did we come to understand that the Milky Way is not the universe, but one of many galaxies, each with its own stars and worlds. In that realization, our sense of place changed forever. To live in the Milky Way is to live in a system that has been forming and reforming for billions of years. Our galaxy was born when smaller proto-galaxies merged in the early universe. Over time, it grew by pulling in gas, dust, and smaller satellites. Even now, that process continues. Streams of stars, remnants of long-absorbed galaxies, weave through the halo. The Magellanic Clouds, two dwarf galaxies visible from the southern hemisphere, are slowly being drawn in, their gas feeding the Milky Way's outer regions. In the far future, Andromeda will join this collection, merging with our galaxy to form something new. From inside, we won't see that merger as a single event. It will unfold over billions of years. The night sky will change slowly, Andromeda growing larger, the Milky Way's shape distorting, new clusters of stars forming where gas clouds collide. Eventually, the spiral arms will dissolve, and the galaxy will become an enormous elliptical. Long after the sun has burned out, the Milky Way stars will continue to orbit within that new structure, their light blending into one diffuse glow. Our galaxy, in the end, will become one of the large luminous forms we now see in distant clusters, another piece in the universe's long history of merging and growth. But for now, we are here, within it. Our Sun is about 4.6 billion years old, roughly halfway through its stable lifetime. Around it, the planets circle, their orbits steady. The Earth, small and blue, spins once every 24 hours, carrying its surface from daylight to darkness and back again. From space, that rotation looks like the slow turning of a glass sphere. Clouds drifting across oceans, continents illuminated in alternating halves. From the surface, it feels ordinary. Sunrise, noon, sunset, night. Yet that daily cycle is the rhythm of a planet moving through the galaxy, a small rotation within a much larger one. Every second, the solar system travels about 200 kilometers along its galactic orbit. In the time it takes you to breathe in and out, we've moved farther through space than any distance you can walk in a lifetime. And while we move, the galaxy itself rotates, its arms sweeping through space like vast luminous waves. The entire disk turns once every 200 million years, its stars maintaining a rough spiral pattern because gravity and motion are in balance. The Milky Way's arms are not rigid structures, they are patterns of density that move through the disk, gathering and dispersing stars as they pass. Our Sun is currently between two such arms, in a minor spur sometimes called the Orion Arm or Orion Spur. That small corridor of space filled with familiar constellations is our neighbourhood within the galaxy. From that neighbourhood, we look outward. Every telescope we build is an extension of our sight, reaching deeper into the Milky Way and beyond. We have mapped the central bulge, found the locations of star-forming regions, and traced the spiral arms through radio and infrared observations. We have measured the galaxy's rotation curve and discovered that the outer stars move faster than expected, evidence of dark matter, the unseen mass that makes up most of the Milky Way's gravitational field. Even though we can't see it, dark matter defines the galaxy's structure, forming a vast halo that extends far beyond the visible stars. Our solar system, and everything around it, moves within that invisible framework. When you think about that we're surrounded not only by visible light but by a sea of unseen mass, it changes the feeling of our position. We live not at the centre, not on the edge, but somewhere within the thick of it, moving quietly through both visible and invisible realms. Around us, stars are born and die. Supernovae explode, leaving behind neutron stars and black holes. New planets form in clouds of gas and dust, their orbits stabilizing over millions of years. Somewhere in those distant systems, other worlds may exist where beings look up at their own skies, seeing their own version of the Milky Way. They would see the same band of light, but from a different place within it, unaware that we are seeing the same thing from ours. The galaxy's structure is vast but not eternal. Its stars age, its gas is slowly consumed, and its shape changes over time. The Sun's light will fade billions of years before the Milky Way does, but even after the last bright stars have burned out, the galaxy will continue to exist, dim, diffuse, and quiet. For now, though, it is vibrant. The spiral arms still shine with young hot stars. The nebulae still glow with ionized gas. The star-forming regions still pulse with activity. Our galaxy is still alive in the cosmic sense, still shaping new generations of suns. If you could watch the Milky Way over billions of years, you'd see it as a living system. Its arms would drift, its stars would change colour, its satellites would merge. The movement would be too slow for any single lifetime to notice, but the pattern would be continuous. That slow, ongoing motion is the rhythm of the universe itself, patient, balanced, and constant. We live inside that rhythm. Every star in the night sky is a note in it, every orbit a beat, every photon of starlight a pulse from that greater whole. When we think of the Milky Way as home, it's easy to imagine it as something separate from ourselves, a structure we live within, but the truth is, it's not separate at all. We're part of it, built from its matter, shaped by its gravity, sustained by its light. Every atom in our bodies was once part of a star, perhaps several stars that lived and died long before the sun was born. The galaxy's history is our history, written in different language but telling the same story. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it comes from the life cycle of the Milky Way stars. That connection is both humbling and grounding. It reminds us that even the smallest life on Earth participates in something vast. The galaxy doesn't recognize us, yet we belong to it as fully as any star. The light that reaches us from across its arms, the faint glow that arches across the night, is not distant in spirit. It's family light, ancient and familiar. Every glance upward is a kind of return, a moment of recognition that we are looking into the structure that made us possible. And though our planet is fragile and our lives brief, the fact that we can look out at all is extraordinary. Out of the billions of worlds that may exist, we happen to live on one with clear skies, stable orbits, and eyes that evolve to detect the very light our galaxy produces. That combination is not inevitable. It's contingent, delicate, and rare. Yet here we are, perceiving the Milky Way from within, aware of it, mapping it, and even naming it. The galaxy doesn't need us to exist, but we need it. For matter, for structure, for light, for the simple fact of being. So when you look up at the night sky and see that faint milky band stretching across the darkness, you're not looking at something distant. You're looking at home. You're seeing the combined glow of countless stars, some near, some far, some long gone. You're seeing the framework of your own existence. You, here, in the Milky Way, are not separate from it. You are one of its expressions. The thought might seem immense, but it's also quieting. You don't have to reach the edge of the universe to find meaning in it. You're already part of its motion, its history, and its light. The atoms that compose you are as old as the galaxy itself. The gravity that holds you to the Earth is the same that keeps the stars bound in their orbits. The light that enters your eyes tonight has travelled for thousands of years to arrive, and in receiving it, you complete the journey it began. If you let that thought settle, the distances shrink. The universe stops being remote and becomes something you're inside of, something that includes you completely. The galaxy turns, the stars continue their long orbits, light moves outward endlessly, and you, here, are one more mind within it, aware for a moment of what it all means to be part of something so vast and so continuous. The Milky Way carries on, as it has for billions of years, a great river of starlight in which we drift. We are small, but not apart, fragile, but not lost. Each breath, each heartbeat, each glance at the sky is a quiet reminder of that connection. The fact that we are here, alive, within the galaxy that made us. And as the galaxy turns, so do we, moving together through the dark, carried by the same invisible rhythm that holds everything else. The stars shine, light travels, time unfolds, and you, here, in the Milky Way, are part of it, completely, perfectly, and always. You're still here, listening, somewhere on one small planet orbiting an ordinary star inside one quiet arm of one galaxy. Everything we've talked about, the collisions, the clusters, the incomprehensible distances, all of it continues right now, silently, in every direction around you. The universe doesn't pause when we sleep. The stars don't wait for our attention. They keep shining endlessly, as they have for billions of years. The Milky Way turns slowly overhead, its light crossing the atmosphere and reaching your eyes. Every photon that arrives has been travelling for thousands of years, moving through dust, through space, through the gravity of the galaxy, to end its journey here. The light that touched ancient mountains, that passed over quiet oceans, now falls softly where you are. You are part of that process. You exist within the same physics that holds galaxies together. The same gravity that bends space also holds you to the Earth. The same laws that shape the stars let you breathe, think, and rest. The universe doesn't make exceptions. It includes everything equally, patiently. Somewhere in the dark, another world may be turning under its own sun, another being may be looking up, seeing their own band of starlight across the sky. They would not know you, and you would not know them, yet you would both share this same galaxy, this same slow motion through space. You would both belong to the same quiet, unfolding story. In this moment, the distances don't matter. The galaxies, the numbers, the scales beyond comprehension, all of them become one continuous field of calm, the same field that you are part of. You are within it now, resting inside the gravity that binds every atom, every world, every light that shines. Let yourself settle into that thought. The Milky Way moves, the Earth turns, the night carries on exactly as it has for billions of years. You, here, are part of that movement, part of that history, part of that light. You don't have to understand it to belong to it. You already do. So as the stars continue their quiet motion, let your thoughts slow to their rhythm. The galaxy spins, the universe expands, and you remain small, steady, and present within it. Good night, and thank you for being here in the Milky Way.